Hi there.
Hello! Do you know who we are?
We are dreamers.
We act for a sustainable future.
342, ready. Hi, we are.
All around.
The world.
We shape a better life for all. And we connect people virtually and in reality. We are passionate.
We are inspired.
Yeah, we are inspired.
And we never stop growing. We explore new horizons.
And we are game changers.
Because innovation is nothing without
human imagination.
We believe the only progress is human. We are Dassault Systèmes.
Hi there.
Hello! Do you know who we are?
We are dreamers.
We act for a sustainable future.
342, ready. Hi, we are.
All around.
The world.
we shape a better life for all. And we connect people virtually and in reality. We are passionate.
We are inspired.
Yeah, we are inspired.
And we never stop growing. We explore new horizons.
And we are game changers.
Because innovation is nothing without
human imagination.
We believe the only progress is human. We are Dassault Systèmes.
Hi there.
Hello! Do you know who we are?
We are dreamers.
We act for a sustainable future.
342, ready. Hi, we are.
All around.
The world.
we shape a better life for all. And we connect people virtually and in reality. We are passionate.
We are inspired.
Yeah, we are inspired.
And we never stop growing. We explore new horizons.
And we are game changers.
Because innovation is nothing without
human imagination.
We believe the only progress is human. We are Dassault Systèmes.
Hi there.
Hello! Do you know who we are?
We are dreamers.
We act for a sustainable future.
342, ready. Hi, we are.
All around.
The world.
we shape a better life for all. And we connect people virtually and in reality. We are passionate.
We are inspired.
Yeah, we are inspired.
And we never stop growing. We explore new horizons.
And we are game changers.
Because innovation is nothing without
human imagination.
We believe the only progress is human. We are Dassault Systèmes.
Hi there.
Hello! Do you know who we are?
We are dreamers.
We act for a sustainable future.
342, ready. Hi, we are.
All around.
The world.
we shape a better life for all. And we connect people virtually and in reality. We are passionate.
We are inspired.
Yeah, we are inspired.
And we never stop growing. We explore new horizons.
And we are game changers.
Because innovation is nothing without
human imagination.
We believe the only progress is human. We are Dassault Systèmes.
Hi there.
Hello. Do you know who we are?
We are dreamers.
We act for a sustainable future.
242, ready. Hi. We are.
All around.
The world.
we shape a better life for all, and we connect people virtually and in reality.
We are passionate.
We are inspired.
Yeah, we are inspired.
And we never stop growing. We explore new horizons.
And we are game changers.
Because innovation is nothing without
human imagination.
We believe the only progress is human. We are Dassault Systèmes.
Hi there.
Hello. Do you know who we are?
We are dreamers.
We act for a sustainable future.
242, ready. Hi. We are.
All around.
The world.
we shape a better life for all, and we connect people virtually and in reality.
We are passionate.
We are inspired.
Yeah, we are inspired.
And we never stop growing. We explore new horizons.
And we are game changers.
Because innovation is nothing without
Human imagination.
We believe the only progress is human. We are Dassault Systèmes.
Hi there.
Hello. Do you know who we are?
We are dreamers.
We act for a sustainable future.
242, ready. Hi. We are.
All around.
The world.
we shape a better life for all, and we connect people virtually and in reality.
We are passionate.
We are inspired.
Yeah, we are inspired.
And we never stop growing. We explore new horizons.
And we are game changers.
Because innovation is nothing without
Human imagination.
We believe the only progress is human. We are Dassault Systèmes.
Hi there.
Hello. Do you know who we are?
We are dreamers.
We act for a sustainable future.
242, ready. Hi. We are.
All around.
The world.
we shape a better life for all, and we connect people virtually and in reality.
We are passionate.
We are inspired.
Yeah, we are inspired.
And we never stop growing. We explore new horizons.
And we are game changers.
Because innovation is nothing without
Human imagination.
We believe the only progress is human. We are Dassault Systèmes.
Hi there.
Hello. Do you know who we are?
We are dreamers.
We act for a sustainable future.
242, ready. Hi. We are.
All around.
The world.
we shape a better life for all, and we connect people virtually and in reality.
We are passionate.
We are inspired.
Yeah, we are inspired.
And we never stop growing. We explore new horizons.
And we are game changers.
Because innovation is nothing without
Human imagination.
We believe the only progress is human. We are Dassault Systèmes.
Hi there.
Hello. Do you know who we are?
We are dreamers.
We act for a sustainable future.
242, ready. Hi. We are.
All around.
The world.
we shape a better life for all, and we connect people virtually and in reality.
We are passionate.
We are inspired.
Yeah, we are inspired.
And we never stop growing. We explore new horizons.
And we are game changers.
Because innovation is nothing without
Human imagination.
We believe the only progress is human. We are Dassault Systèmes.
Hi there.
Hello. Do you know who we are?
We are dreamers.
We act for a sustainable future.
242, ready. Hi. We are.
All around.
The world.
we shape a better life for all, and we connect people virtually and in reality.
We are passionate.
We are inspired.
Yeah, we are inspired.
And we never stop growing. We explore new horizons.
And we are game changers.
Because innovation is nothing without
Human imagination.
We believe the only progress is human. We are Dassault Systèmes.
Hi there.
Hello. Do you know who we are?
We are dreamers.
We act for a sustainable future.
242, ready. Hi. We are.
All around.
The world.
we shape a better life for all, and we connect people virtually and in reality.
We are passionate.
We are inspired.
Yeah, we are inspired.
And we never stop growing. We explore new horizons.
And we are game changers.
Because innovation is nothing without
Human imagination.
We believe the only progress is human. We are Dassault Systèmes.
Hi there.
Hello. Do you know who we are?
We are dreamers.
We act for a sustainable future.
242, ready. Hi. We are.
All around.
The world.
we shape a better life for all, and we connect people virtually and in reality.
We are passionate.
We are inspired.
Yeah, we are inspired.
And we never stop growing. We explore new horizons.
And we are game changers.
Because innovation is nothing without
Human imagination.
We believe the only progress is human. We are Dassault Systèmes.
Hi there.
Hello. Do you know who we are?
We are dreamers.
We act for a sustainable future.
for two, ready, hi, we are.
All around.
The world.
We shape a better life for all. And we connect people virtually and in reality.
We are passionate.
We are inspired.
Yeah, we are inspired.
And we never stop growing. We explore new horizons.
And we are game changers.
Because innovation is nothing without
Human imagination.
We believe the only progress is human. We are Dassault Systèmes.
Hi there.
Hello. Do you know who we are?
We are dreamers.
We act for a sustainable future.
Two for two, ready, hi, we are.
All around.
The world.
we shape a better life for all. And we connect people virtually and in reality.
We are passionate.
We are inspired.
Yeah, we are inspired.
And we never stop growing. We explore new horizons.
And we are game changers.
Because innovation is nothing without
Human imagination.
We believe the only progress is human. We are Dassault Systèmes.
Hi there.
Hello. Do you know who we are?
We are dreamers.
We act for a sustainable future.
Two for two, ready, hi, we are.
All around.
The world.
we shape a better life for all. And we connect people virtually and in reality.
We are passionate.
We are inspired.
Yeah, we are inspired.
And we never stop growing. We explore new horizons.
And we are game changers.
Because innovation is nothing without
Human imagination.
We believe the only progress is human. We are Dassault Systèmes.
Hi there.
Hello. Do you know who we are?
We are dreamers.
We act for a sustainable future.
Two for two, ready, hi, we are.
All around.
The world.
we shape a better life for all. And we connect people virtually and in reality.
We are passionate.
We are inspired.
Yeah, we are inspired.
And we never stop growing. We explore new horizons.
And we are game changers.
Because innovation is nothing without
Human imagination.
We believe the only progress is human. We are Dassault Systèmes.
Hi there.
Hello. Do you know who we are?
We are dreamers.
We act for a sustainable future.
Two for two, ready, hi, we are.
All around.
The world.
we shape a better life for all. And we connect people virtually and in reality.
We are passionate.
We are inspired.
Yeah, we are inspired.
And we never stop growing. We explore new horizons.
And we are game changers.
Because innovation is nothing without
Human imagination.
We believe the only progress is human. We are Dassault Systèmes.
Hi there.
Hello. Do you know who we are?
We are dreamers.
We act for a sustainable future.
242, ready. Hi. We are.
All around.
The world.
We shape a better life for all. And we connect people virtually and in reality.
We are passionate.
We are inspired.
Yeah, we're inspired.
And we never stop growing. We explore new horizons.
And we are game changers.
Because innovation is nothing without
Human imagination.
We believe the only progress is human. We are Dassault Systèmes.
Hi there.
Hello. Do you know who we are?
We are dreamers.
We act for a sustainable future.
242, ready. Hi. We are.
All around.
The world.
we shape a better life for all. And we connect people virtually and in reality.
We are passionate.
We are inspired.
Yeah, we're inspired.
And we never stop growing. We explore new horizons.
And we are game changers.
Because innovation is nothing without
Human imagination.
We believe the only progress is human. We are Dassault Systèmes.
Hi there.
Hello. Do you know who we are?
We are dreamers.
We act for a sustainable future.
242, ready. Hi. We are.
All around.
The world.
we shape a better life for all. And we connect people virtually and in reality.
We are passionate.
We are inspired.
Yeah, we're inspired.
And we never stop growing. We explore new horizons.
And we are game changers.
Because innovation is nothing without
Human imagination.
We believe the only progress is human. We are Dassault Systèmes.
Hi there.
Hello. Do you know who we are?
We are dreamers.
We act for a sustainable future.
242, ready. Hi. We are.
All around.
The world.
we shape a better life for all. And we connect people virtually and in reality.
We are passionate.
We are inspired.
Yeah, we're inspired.
And we never stop growing. We explore new horizons.
And we are
tout seul. Ouais. Okay, take a seat, please. Don't be shy. You can go in front of the stage. No worries. You won't go on stage, so, except for the ones that are already scheduled. No worries, no worries. Bonjour, welcome to everybody. Really pleased to welcome you at in our campus for that first event. This is the first time we are organizing such kind of event for from a CATIA standpoint. I mean, so related on infrastructure and buildings. So CATIA is well known, you know, to talk about mechanical, especially in V5. We are coming from aircraft, etc. The purpose today is really to show you what we are able to do related to infrastructure and buildings. Really to show you that with CATIA 3D Experience Platform, we can help on the transformation of that sector. And this is why, in fact, so we will co-animate this session with Robert, that is on the right, just to show you, in fact, I hope, full scope of capabilities from a CATIA standpoint. And in terms of agenda, so as you could saw it, today will be dedicated to infrastructure. So in the morning, so it will be more sessions dedicated to infrastructure, energy, and materials industry. Then we will have on the afternoon more manufacturing sector oriented sessions. So in the morning, more oriented about let's say civil linear infrastructure. Then we will have information related to energy, and so on the afternoon, more dedicated to all that is related to factories, gigafactories, semiconductor factories, but as well about data centers. And we will finish the day with a session dedicated to R&Ds, so two main R&Ds helping us on that transformation, meaning the CATIA construction R&D and the CATIA system R&D, that we share with you, in fact, their vision and the highlights. And tomorrow will be dedicated to buildings, and so mostly to architecture, engineering, and construction industry. So we will talk about the transformation that is ongoing, led by this AEC industry and with building construction. And so we will have a customer testimonial with CSADI from China. And then we will continue with facade makers and as well with urban planning capabilities. And as well, we will finish with dedicated session for R&D to talk about vision on building strategy. But let's start first of all with the opening from our CATIA CEO. Unfortunately, he's not able to participate today due to another session in Germany. So I will just play the video he registered recently.
Good morning. Welcome to our workshop dedicated to infrastructure and buildings for organized by the CATIA brand and with participation from industry. And I would like to thank you very much. I know we have several companies from these important industries today and tomorrow. Today for more infrastructure type of projects, and tomorrow for architecture, construction, buildings. So I'm very glad that we could organize that. So what are we trying to address in terms of challenges? First, we want to address the complexity of your project, making sure you can get full traceability of what you do at any stage of the process. Collaboration across teams within your ecosystem, making sure that all the CATIA process that we want to cover, solution and processes, are integrated in the 3D Experience platform so that you can get this kind of collaboration across the team. Anticipate all operation and maintenance activities by having a system thinking from the beginning of the project. And finally, reducing time for design engineering by mastering design at all levels of detail, from the start of the project until certification, operation, and maintenance. So one of the questions you may ask yourself is why CATIA, which was for many years the reference more for the automotive sector or the aerospace sector, where there are key values today that we can bring to infrastructures and buildings. First of all, CATIA is smart because we are investing a lot on system. even on system of system. Why? Because we think that in the very early stage of every single programs, there is a need of a system view from requirements, functional view, logical, until the physical realization and implementation. And this system view is critical, by the way, not only to define the project itself, but also to define the industrial environment, such as factories. So it's a first very important point. The second one is CATIA is modular. More and more, your different projects are going to reuse a lot of modules, going through productization. So for many years, CATIA had this concept of templates that you can reuse across different programs. So the goal here is to make this modularization available for big and large energy, infrastructure, construction projects. And the last one is generative. Everybody is talking about generative design, artificial intelligence, and of course, the power of CATIA is really to bring generative at every stage of the project. We are investing since many years on generative design. One example is, for example, we work with on facade design with many companies to accelerate the design in a generative way. And of course, artificial intelligence based on all the content, all the knowledge you accumulate in all your companies is going to be crucial to stay competitive in the future. So I hope you're going to discover a lot of this during the different session. Enjoy the conference. Take time to exchange with experts, to discuss with your peers from the different sectors. I know there are a lot of people who have accepted to share their experience of using our 3D Expanse platform and CATIA on their projects. So there is a lot of things to learn. Sorry for not being with you today. I'm traveling to Germany, where we have a big conference as well with our German clients. I hope I can be with you next time, and I'm sure you're going to have a great conference. And so back to you, Corinne, Rémi, Olivier, Stéphane, for this great conference. Bye-bye.
So now, welcome on stage. Please welcome on stage Corinne Bulota, so our INM VP, to talk about the vision for infrastructure, energy, and materials.
Nice crowd. Welcome. Nice to see you all. So thank you for the introduction, Olivier. I'm Corinne Bulota, the Vice President for Infrastructure, Energy and Materials. And my challenge in this introduction, my job will be not to spoil the presentations of my colleagues and partners coming after me. So I'll try to stay high level, but give you an overview of what we see as being the priorities in the infrastructure, energy, and materials industry, and what are the focus and ambitions. So you might have seen this. It was shared with the market in 2022. It's the ambition that Dassault Systèmes has set for itself in its three sectors. So you must know our legacy. We are leaders in the PLM world, in the manufacturing sector. We are growing fastly in the life and science healthcare with the acquisition of Medidata that gave a big boom to this sector for us. And we are very serious and ambitious in terms of gaining a strong footprint in the infrastructure and city sector. We have set for ourselves an ambition to grow that is bigger than what the market is showing. So just to answer often the questions I receive, how serious is Dassault Systèmes in this sector? I can tell you that we have a strong ambition to become a leader in that sector on solutions that we believe will be the catalyst for the transformation of the sector, but also for the energy transition and the decarbonization that this sector has to go through. So infrastructure, energy, and materials. We've divided this industry in three pillars. Sustainable infrastructure, which encompass all the linear large infrastructure. In this pillar, Dassault Systèmes, we are specifically focusing on rail tunnels. Why? Because for us, rail is the level of complexity that an infrastructure project can get to, that we really can bring value. I think Olivier said it in his first sentence. Where does Dassault Systèmes really bring value to their clients? And it's when the projects are complex. And a rail project is not only a civil infrastructure project, it's a system project. So there's so much interfaces between the systems, the stakeholders. This is really where we think we can bring value in addition to what the designers and the builders and the operators and maintainers are already doing in the digital space. In terms of clean energy, this pillar, it's strongly supported by our footprint in the nuclear industry. We are a leader in France, UK, in terms of delivering PLM solutions to the nuclear sector. We are starting to get momentum in other parts of the world. It's a very private sector. It's difficult for us to really discuss what are our partnerships, who are our customers in this space, because it's a very secured and private sector. But we're moving fast also in the small modular reactor and advanced modular reactor space, where we're building strong momentum with the conventional owners, operators, but also with the startups that are developing, as we speak, new technologies. And the third pillar is decarbonization of process industries. So we have under this pillar the mining companies, the metals and minerals companies, and the chemical companies. And why, we could say that those three sub-industries are very different one from the other. In fact, where Dassault Systèmes is focusing is really helping those companies in terms of defining their roadmap to decarbonization and to net zero. So where in mining, we have brands like Geovia very involved in the upfront part of exploration and mining exploration, where we're adding more value. It's with the 3D Experience platform and creating this single environment where all the stakeholders around a mining exploration will use and elevate the information and the data to take better decisions in terms of reaching sustainable and efficient operations. So what does the industry renaissance means for our customers in infrastructure, energy, and materials? We believe that with our multi-scale virtual twin experience approach, that allows not only science and design, but also business and technical innovation, and most importantly, knowledge and know-how capture, will be actually the catalyst of this transformation. We've seen most of those actors in this sector, taking decisions and transforming for the last 15, 20 years, but it's still very siloed. It doesn't encompass usually the whole life cycle of the infrastructure assets. We have solutions, that serves the design phase with project management, document management, but we haven't seen a real, even if there's standards, if there's visions, we haven't really seen a real experience that goes from the design phase to the operation and maintenance phase with the same, set of information and data transferring from one phase to the other. So we really believe at Dassault Systèmes that the platform, the 3D experience platform, and the virtual twins experiences will be the catalyst for breaking these silos and bringing the stakeholders much closer in terms of collaboration and in terms of efficiency. So if we only take the example of power generation, we know that it is currently responsible for 25% of global GHG emissions. And in this context, we've been leveraging our multi-year experience as a strategic partner of EDF France. We have Marianne with us today. We have EDF with us today. So it's really with this partnership that we have been able to create a reason to believe and convince ourselves that we could actually be a real partner and a real, I would say, challenger, but in a good way, a real challenger of what the innovation can be in this sector. And this has allowed us to gain in credibility and in presence in the whole nuclear sector. And our customers are not only using our solutions for R&D and design, but as Olivier said, for modular fabrication, for plant construction and commissioning, and for certification, so digital certification. I want to give you a customer testimony. We have become the partner of the UK Atomic Energy Authority in late Q4 last year, and I'll give you his testimony for why UK has chosen the 3D Experience platform and our solutions to deliver their project.
Yeah, the UK has a fusion strategy. I'm not sure people are aware that we have a fusion strategy. And part of that strategy is, well, first of all, to build a power plant, a prototype power plant, fusion power plant. But more importantly, is the second goal, which is around building capability to build that first-of-a-kind power plant. So on STEP, I think it's really important to understand this as first of a kind. It is a prototype power plant, and it won't have any physical tests necessarily to demonstrate that it's a viable thing. So we are going to have to digitally qualify our power plant. So what's so important for us is to have a platform that enables us to do that qualification process and reassure ourselves that it is going to work as we predict, and that it's important to stakeholders that they have that confidence that it's going to deliver what they've invested in. You know, what we want to try and create is something which is bigger than the individual organisations. This is about building a national equity and about lots of different organisations to be able to work together in a seamless way with no barriers, and hopefully that collective can produce this first-of-a-kind power plant.
So what's interesting with UKEA is that evidently they start with the usual applications needed in the nuclear sector. Document management in a configured way. I say document, but it's data management in a configured way. But they're really looking at creating this foundation to do more with it. Why? Because, as they said, they have to build a first of a kind, which would probably have needed in the past multiple prototypes before being able to launch, the final product or project. But they're really looking, as we've done it in the aerospace sector, they're really looking at using the virtual twins to simulate and to commission their product before having to actually do the physical testing on the chosen solution, on the chosen prototype. So it's much more than just creating this single source of truth. It's elevating the information and capturing the knowledge and capture to accelerate the development. So again, we are in a CATIA event. You're probably asking yourself, she's talking about the 3 days for platforms. She's talking about virtual twins. What about CATIA? Well, again, maybe spoiling the punchline of my follow presentators, but we believe that there's no virtual twin without having initially a strong model-based system engineering virtual twin. So the goal is absolutely to have a virtual twin as built in operation, virtual twin, to really bring the value that our solutions and application can bring to our customers on the long span of their operations. But it has to start, in our mind, with model-based system engineering. And this is the first, it's not a separate virtual twin, but it's the first layer of a complete virtual twin. And we're currently working, we'll not talk about infrastructure because we have a presentation just following, but we're really where we are starting to engage on large capital projects that are delivered with collaboration of public and private partnership, is really we're engaging first with this idea of creating the virtual twin of the system of systems. And in systems, I'm not only talking about technical component of the system and the assets, but I'm also talking about the stakeholders. We're also building the virtual twins of all the stakeholders around the project, and what is the interface between them, between their contracts, what is the impact of their role and mission in the definition of the project. So today, I hope we will be talking a lot about system engineering, system thinking, system engineering. It's not a sexy world. It's much more interesting to see, 3D models that are very complex and detailed. But system engineering is so important to this sector, which has not been used to work with a global view of the requirements and the performance criteria of their project at the initial phases of design. So I hope you'll have a great event. This is important. We have partners and customers that join us for this 2023 session. We're very proud and happy to have you all here. Have a great event.
Thank you, Corinne. And if you remember the three pillars Corinne was talking about, so let's continue with sustainable infrastructure. And so please welcome Eric Gardon from Colastrai and Stéphane Aubert and Yaro Baudi from Dassault Systèmes for the next session.
The laptop is coming. So a quick introduction. My name is Stéphane Aubert. I'm a business consultant at infrastructure at Dassault Systèmes.
I'm Eric Gardin, lead of BIM and project manager for a national project I represent.
Hello everyone, my name is Jacob Audi, industry process expert, CATIA brand. And, yeah,
It's not. C'est bon? Ça vient, ça part. C'est bizarre.
je vais essayer ici.
Un instant. Et vous arrêtez un compteur?
Mais il veut pas. Non, ça veut pas. Vas-y.
Perfect. So railway infrastructure is one of the most complex infrastructure within, in the transportation industry. And we believe in Dassault Systems that we have technologies allowing to make this infrastructure more smart and more sustainable. And I'm pleased today to co-present with Eric Gardon from Colas Rail, who is lead of BIM and project manager of EMEA project, and also with Stéphane Aubert, who is business consultant from the infrastructure, energy and materials industry. Today we will go through the life cycle management and our strategy for this industry with Stéphane. And as Corinne mentioned, MBAC, Model-Based System Engineering, is one of the pillars of our strategy to transform this industry. So I will go through the strategic business model, data model for this model-based system engineering. And then I will let the floor to Eric to present Colas Rail and the Minerve project. Sorry about that. We will switch the computer. Non mais vas-y, si t'as ton ordi, c'est bon.
commencer avec comment, Stéphane, pour gagner le temps?
Thank you, Jarob. So what is infrastructure? Corinne mentioned this morning, we're organized by brands and by industries. So with the I&M industry, and this session will focus on infrastructure. For us, in this space, infrastructure is what we call horizontal infrastructure. So it's typically like a road, rail system, bridges, can be a dam. We'll focus mainly on rail and why, because as Corinne mentioned, and again Jarob, it's probably one of the most complex systems in infrastructure. It's a mix of civil engineering, it's a mix of power, electricity, power traction. It's a mix of systems like a signal system. So it's probably the highest complexity in linear infrastructure. What is interesting in infrastructure compared to traditional manufacturing space, where Dassault is coming from, the PLM, product lifecycle management, is infrastructure is typically a very long life cycle asset. We are commonly talking 100 years. What is always very complex in infrastructure are the stakeholders. We're on a very long lifetime, and you have multiple stakeholders in infrastructure. Everything starts with design. You're designing actually for construction. We would hope we design for them, but it's most of the time not the case. Once the design is pushing the information to construction, there's a handover process, which is quite complex to handle. Construction then is building. They may tweak the design, they make some changes. They have to build all the logistics for 4D planning behind the construction. Same thing, once everything is built, there's a handover to the O&M company. Again, there's a switch of information. And at the end, we will operate and maintain infrastructure. We'll sometime go back to design and build. Let's say in 50 years you have to rebuild a major bridge. You probably have to redesign and rebuild the bridge. But you can stay in the maintenance space to do classic maintenance, like for example a road or rail, and make some ballast changes or rail changes. This doesn't need to go back to design. So we have in front of us a very complex life cycle with a lot of stakeholders, and we have also what is called greenfield and brownfield projects, because this space is organized in different markets. Greenfield, basically new infrastructure. Brownfield is an upgrade of the update of existing infrastructure. But you also have different stakeholders. You have company managing existing infrastructure, like in France the French SNCF or Deutsche Bahn in Germany for rail. But you have also a market organized around projects. HS2 is a good example. It's a project, and typically everything is organized around this project. Design, build, and then will be pushed to the O&M company. So high complexity in the stakeholders, high complexity in the handover sessions between all the stakeholders, and high complexity because you have to mix different systems. So basically system-to-system approach. When talking to our infrastructure partners and clients, worldwide we see actually the same issues. And this market has been quite low to transform into digital. When I joined a few years ago a soft division of the Vélizy group, I think construction was a second latest industry in digital transformation. I think fishing industry was just behind. I think fishing is today before construction. But construction is only one phase of this global infrastructure. So we are not focused on in construction. It's really basically to have a full picture of infrastructure. And the feedback we get from most clients are basically shown on the left side of this slide. More and more infrastructure agings, either we have to rebuild them or we have to move to greenfield. With environmental pressure, the idea is really to try to rebuild as many infrastructures or reuse material. But typically, people are looking for infrastructures. More and more we build new rails or we update rails. We're still building new roads. So this is really a growing market, but we have this problem to actually manage all this infrastructure today. So it's not only a greenfield view, it's only a brownfield view. There's a pressure on cost, and I think this is at all the level for construction, for O&M, there's a pressure on cost. You have to do more with less, so people have to find ways to be more productive and to be able to manage better all these assets. There are also new ways of managing assets. There are new ways on the construction side, mainly coming from software changes. There's also higher complexity in the asset side. To manage multiple systems is an issue. I still see a lot of DOTs worldwide, Department of Transformation, working on silos. They have a team specialized on bridges. They have a team specialized on signal systems. They have a team specialized on power traction. So this may go on, but still you have to find a way to have this complexity be managed easily. There is a strong pressure also on sustainability. This is becoming strong at any level in the asset during construction, losing to low carbon concrete, for example, but it's also the way the infrastructure is managed on the O&M side. We're more moving to models of asset, technical models, but also financial modeling of assets. And last and not least, this market has issues attracting people. Engineers love to work in the IT space, the financial space. In the US, North America, a lot of people actually are not attracted by infrastructure. It's less of a problem in Europe. But at any stages, design, construction, and O&M, we have problem attracting new talents. And we're losing more and more workforces, and we're losing something very important. It's the know-how and knowledge of its people. Data is not really the issue is really the knowledge. And we will see how we want to capture the knowledge in the next example. So what's our strategy? We try to find answers to these key points. I would say it's like a Saturn V rocket. It's a three-stage approach. Virtual twin, Corinne mentioned a few minutes ago our virtual twin approach. I will go into more details. Science-based and collaboration. Collaboration is quite easy to understand. It's basically a platform. And it's not only a technical platform. It's a platform where people can share knowledge, can share information. It's more than a CDE. It's typically a platform where you can mix multiple information, structured information, unstructured information, same thing for databases. You can work with multiple databases. You can work also with multiple tools from third-party companies. The platform is open. But the platform is really key in our strategy. This will allow collaboration at any stages of the asset lifecycle, design, build, O&M. And typically this platform could be put in place during the design phase to allow the O&M company to provide input as early as possible. The idea behind this three-stage approach is basically to optimize and de-risk the infrastructure project or the infrastructure maintenance by building a virtual twin in a platform, so open to all the stakeholders, and using what is a science-based approach, basically a mix of big data, a mix of artificial intelligence to basically bring knowledge to the platform. Before going on, I think it's very important to understand what we mean with a virtual twin by Dassault. You see a lot of articles about digital twin, virtual twin, but I think it's very important for you to understand how we see the virtual twin and how our approach is important to have a global view. So let's imagine you're in the design phase, and the first thing we will do basically is move to an MBSE approach, model system-based engineering. There are multiple reasons for this. First, we'll work in the logical functional space, and Yarob will provide more details, but basically the MBSE is a foundation to the start of a virtual twin. We'll get the requirements, will build actually the whole infrastructure in a logical space, and we're moving more and more to an object model. Why object is so important? Because actually you can simulate an object. I cannot simulate a BIM file. I cannot simulate a document. So the object-based approach at MBSE is key, and it's also key for the O&M company. When you manage the infrastructure, the first thing you have to do to manage is basically have an inventory of your infrastructure. So you're basically object-based. And this is a link, starting with MBSE is basically the start of our digital twin, virtual twin, and it's also a start for the O&M company to be able at early stage to provide input to the design. This is really the most important part is MBSE, and MBSE is basically the CATIA brand is providing the tools. Second thing is the process. You need the process in operation, in construction. I'm starting here in design, so I'm not talking about the design process. But without the process basically the knowledge is how I'm going to build this, how I'm going to maintain, how I'm going to replace a piece of equipment. Just imagine you have to change a bearing on a bridge. How do I reach this bearing? I will have to go back to a real space. So what's the process doing this? Our key is simulation. And simulation can be done at very early stage. In basically MBSE, today you can simulate an asset, you can simulate a bridge without actually building the bridge. You see it in the PLM, product lifecycle management. When you build a new car, a new plane, the plane can be basically simulated at very early stage without building the car itself. When you build the car, when you build the plane, it's flying the first day. So simulation is key, and you can simulate construction, you can simulate O&M, you can simulate an object, you can simulate a train, but basically there is no limit in simulation. It's a multi-scale, multi-level simulation, can be electrostatic, can be a physical simulation. There's a wide variety of simulation within the CATIA brand. Monitoring is key. Two ways to see monitoring. When you're in design phase, you may use big data information to see aging models, for example, for a bridge, a bearing. But you can also use, once you have built the system, use sensors. Typically, you see it a lot for major bridges. Construction O&M companies put sensors to see if a bridge is reacting like the design phase. So in the design, we did simulation. We're moving to construction, moving to O&M, the bridge is built. We put sensors and we see if a bridge is actually reacting like the design. If design and real life is the same, the bridge will normally follow its physical life cycle. If not, you have to redo calculation and rebuild your O&M plan. And so monitoring is key, not only real-time monitoring, but also information coming from big data, because I can basically build aging models based on information from multiple sources. And we have a brand called NetVibes, who allows our client to extract information from the web or from documentation, maintenance documentation. There's basically no limit. At the end, once you're happy with the design, the maintenance, the interaction between the system, you go back to the physical space. You basically go back to design, or do 2D design or 3D design, and for construction. The interesting thing with virtual twin is you can build different type of virtual twin. You can build a virtual twin for construction, you can build a virtual twin for operation, and you can build what we would call virtual twin system of systems, having a global view of all the different phases and all the different type of systems. So to go more in details, Jarob, can you please explain the MBSE approach?
Absolutely. So the railway infrastructure is a system of systems. What that means, we have the infrastructure itself as a final system or final product that we want to build, we want to operate, but we have also what we call enabling system. We will need, in fact, an ecosystem to design, to build also, and to operate this infrastructure. This enabling system, which is all the stakeholders involved within this project from a very, very early stage of the project, from the feasibility studies, for example. We need to understand their responsibilities, the interfaces also between the different work packages, for example. What are the main objective? What are the why we are building this infrastructure? Is this infrastructure meeting the main needs and the main interests we will envisage? So everything should be structured within the same data model, which will be able to support the whole life cycle of the infrastructures. With CATIA Magic solution, we will be able to map all the ecosystem from what you see at the left of the screen or of the data model. So this ecosystem will be able to understand the different interactions between the stakeholders, but also to get all the work packages, to structure all the requirements, which will at this stage be high-level requirements. But after that, we will specify them. We will understand what are the different market standards, for example, that we need to respect to build this infrastructure and to operate this infrastructure. Coming after the requirements, all the functional architecture, the logical architecture that we need to integrate within the same model in order to specify more and more and to get more and more this design detailed. And after that, we arrive to the physical or to the engineering item, what we call on the market BIM, building information modeling. So we will be able to link all the diagrams from the logical architecture to the physical structure of the asset. And that will allow us to have a clear idea about the infrastructure, how we want to operate them. So we will need even how we want to build them also. So we will be able to link all the processes of the construction, of the operation, of the maintenance also, and be able to, to get the virtual twin of the operation and maintenance, what Stefan just mentioned before. For all these physical components and processes, we will be able to link resources, what we will need as human resources, as materials, for example, but we will be able also to simulate all the costs related to these different processes, all the environmental impacts, for example, to get really optimize the design, optimize the operation in order to decrease this environmental impact. So there will be a lot of possibilities that we will be able to run simulations on this model-based system engineering, and it will be also covering the whole life cycle of the project, which is very powerful at this kind of infrastructure. As an example, I wanted just to show you quickly a tunnel project where we have, with our partners, we have structured all the requirements of this tunnel project. And when I say requirements, it's really the final customer requirements, but also the technical specifications, the market standards. So we will be able to link all these different levels of requirements, and we will be able to pilot the design with these requirements. So all the parameters, for example, coming for the, for the dimensions of the tunnel, the diameters, whatever the parameter is, we can integrate it and pilot it from the requirements. On the functional level, what we see at on the tree at the left of the screen, we will map all the expected missions of this infrastructure. We can imagine that in this tunnel, we will have one day a major crisis, an accident in the tunnel. How all these systems should work together in order to manage this situation. We will be able to close the tunnel, to run the firefighting system, for example, to call automatically the firemen, for example, etc., etc. So all these systems should work together, sometimes automatically and sometimes maybe manually. So all these interactions should be expected in order to help the final customer for the commissioning. We can maybe do a virtual commissioning before to do the real commissioning. On the logical side, we'll have all the diagrams of all the systems, signaling systems, electrical system, drainage system, whatever, and we will understand all the interfaces between these different systems and also the responsibilities of each subcontractor or each a specialized company working on the delivery of each system. And on the physical, of course, we will have all the BIM model, so all the 3D model. It could be coming from CATIA, from, could be built 100% with parametric capabilities on CATIA, but it could be also coming from a external software. So we have the openness of the platform to get all the data outside of the model and get this RFLB model as a skeleton of the virtual twin that we will build all the different, structure all the data of the project. What you see now on the screen is the system traceability. All data will be, will be traced. We will have a full traceability on all the data, and we will have a 360 vision of all the data of the project. So we will be able to understand the impact of each change, if we want to change something, or if we want to run the what-if scenario. So if we will understand what are the impacts of this change, we will be able to simulate. We will be able to understand which part of the infrastructure maybe will be impacted, if anything could happen. And also, we will understand all the specification that we will implement in the design, which requirement or which customer requirement will meet. So we will be able to cover all the customer requirements, and we will be able to get that commissioning much more efficient and much more quick. So that's it from my side, and I will let the floor to Eric.
Thank you, Jarob. So I propose to this agenda to present my company and the project. What are our expertises in rail? What is the MINERV R&D project, and what experiment we are conducting with Dassault Systèmes? So, as I said before, I'm collateral lead of BIM, and I'm project manager for MINERV, and we'll see what. So what our expertise is, Collateral works as a railway integrator able to deliver turnkey railway projects in design, in construction, and maintenance. In design, for example, we have at the moment the Manila Metro project in the Philippines. As a construction, we have already done the metro line of Rennes and Lyon also. And in maintenance, we are in maintenance during several years of the high-speed line between Nîmes and Montpellier. We perform 12 domains. So in this nice picture, we can see them, but I will focus on seven of them that are subsystems of a system infrastructure, of a railway infrastructure. This is, you can maybe try to find it. This is the civil engineering, of course. The railway signaling, we see at the top. You have also tracks, different type of tracks. The distribution substation, also depending on the voltage you want and the system you want. You have the low voltage and telecom for lines control centers. So this is exactly what can be found in a vehicle, all low voltage systems. And we have electromechanical and safety equipments, mainly internal and stations. And at the end, you have overhead lines for tramway or train. So all these domains are covered by 6,000 people and in 30 countries. So now focus on what's MINERV. MINERV is a national project that stands for Methods and Tools for Sector Collaboration and Digital Continuity over the Life Cycle. So it's very complex, because MINERV is simple. And MINERV is funded by the government. It's part of the France 2030 roadmap. So what's the goal? The main goal is from BIM, the Building Information Modeling, to create the digital twin of French railway network for SNCF. But there's also a lot of intermediate objectives. And it's important to understand the philosophy. First of all, we develop design and construction method and tools using BIM. And we anticipate the site work with that. Then at the end of the site work, we have a has-built. And the has-built we will test it. We create the digital twin. And we will use this digital twin, the project will use this digital twin to improve resilience to climate change. At the same time, we developed, and it's part of what I will present after, to develop an industrializable and standardized and shared vision of the interfaces, ensuring the digital continuity via the BIM model on all phases. And we cannot see the end, but we build a collaboration ecosystem around the modeling and around all stakeholders of ecosystem of a railway. So this is the objectives. Now, what is the meaning of consortium? This consortium is built for until 2026, and it's created by 6 entities and led by SNCF Réseau. All the railway sectors contribute because we have the organization with subcontracting with all different companies in the circle that works and that contribute to this project. And we can see we have the main engineering and construction railway, French railway companies. The project organization. The project organization is split into 2 main work packages. So, as you imagine, the building information until the creation of the digital twin. We settled that digital twin for us, for railway, is beginning when you have a real infrastructure, when you have a real and the virtual, so you have a digital twin. Before the creation of the infrastructures, even if it's a platform with a twin, with a virtual design, it's not called a digital twin. So you can see different type of tasks. All the work packages are divided in tasks, and different tasks are led by different companies. And you can see that it started from tools in 1.1. It go at the end in 1.7 by the railway operation platform. So it's a BIM platform, so as usual, but this one will be specified with a specific railway requirements for sectors that totally does not exist for the moment in the current CDE or platforms. And at the end, there's the creation of a digital twin. So we can see four big tasks. Decision supports for maintenance. So sorry for the display, it's not very visible. Decision support for maintenance. Laws of aging, so research on that. Adaptation of a transport plan following an incident. So it's the aim to use artificial intelligence to propose a solution to traffic as soon as an incident occurs, and then you can, and then with the digital twin, you can specify and you can reorganize and propose reorganization. So this is, of course, these deliverables will not be public. It will be restricted to SNCF. And the last one is a climate change resilience with a Kairos startup that is specialized in satellite imagery that can combine with a digital twin, and to follow what happens on the ground with effects of storm, water, and so on fire also on summer, and then that combine into the data with a digital twin. So the digital twin capped data from around the situation he feels and the situation he has, and then it integrates into the digital twin to take decision. So this is the main presentation I've done for the task in the project. So we will focus on 1.3. 1.3, I lead that for the consortium. We experiment concurrent design methods, and that's why I take the idea to work with a Dassault System for that. So experiment with concurrent design methods. So these experiments are 3 experiments. Collateral, I will lead 3 experiments. First one started 1 month ago. It's with SNCF, the European Rail Traffic Management System, signaling system. This is the context, and we will use MBSE for creating the design, the preliminary design, we said, preliminary design of this project. Second one is the Colastrel team that works with Dassault. For a multidisciplinary railway system context, it will be a new railway, new train station. So I will explain after. And the next one in 1 year ago, it will be Nexteo signaling context for RATP. Nexteo is the same train traffic management system, but dedicated to connect train design from RATP to train design from SNCF, so especially for RERB that covered the two sections. So all these experiments will be public deliverables at the end of a project. So what are main steps of experiment? First of all, Colastrel team had been trained on different tools as 3D experience, CATIA Magic for MBSE. Second one, our system experts model the railway system and the subsystems problem of a new train station. Thirdly, the solution is modeled with MBSE and BIM tools. Then, between us and Dassault, we have co-decided to test 10 use cases that represent a real way of designing the infrastructure. So I will not go through this use case, but we'll test the traceability, the impact management of a change, because in a sector, the change occurs every time. As the project is so long, in a real project, it could be covered 10 years, a project, and the start of different subsystems are not synchronized. So it's a pity, but for example, in a Grand Paris Express line in line 18, not far from here, the stations are quite finished, the civil work are quite finished, but the railway system has not started. So as soon as we started, our requirements are not, of course, in line with design architectures of a station. And we say it's not possible and we need to change. And it's years and years of modification and civil work, rebuilt of civil. So it's a problem of organization of project, a problem of cost, a problem of there is not a view of global requirements, a view of global data. All is splitted, and all is paper-based for the moment. And the 5th one is to define the railway ecosystem concurrent design method. So this is very important to find something that equivalent that we can I can have seen in a car industry before I was in car industry, the concurrent design. So this is the result. We are still working on that. So this is our new train station, Nice Airport Station. So the team, the technical management office of Colastrel are organized in teams according to the rail subsystems. So you can see different track team, signaling team, traction power team, and catenary team, and all together with a system integration team. We are all working around the 3D experience, and of course, and thank you for your help, Dassault manage the training and the assistance and the method, return of experience of the method of system of system and subsystems. And we are helping also them to understand what is infrastructures and railway infrastructures, because it's not easy to make the link between what is done in other industry. The closest we can have imagine is naval problematics for submarines and so on. It's quite the same way of work. So space allocation, for example, is the way we are working in BIM, because as the systems communicate with others, with interfaces, a lot of interfaces, and a space allocation in different place. So at the end of this project, so it will be finished in 5 months. It will be quick. It's a quick win project, and we are still into design for the moment. So at the end, the aim is to create the first full digital engineering process for railway preliminary design. So it's preliminary design, it's not complete design, but this, the goal is to have these first steps. So I don't know if it's in other countries they have achieved it, but for what I know, in France, it's the first time we start the digitalization of this part of a design. So, thank you.
Do you have any question? Is there any question for this session?
So for the next year, we can count that because of the Colas Trail, we won't have any delays in SNCF in France.
Hope so.
Yeah. Any questions? No questions. Everything was perfectly clear, right? Thank you very much once again. For the next speakers, I will just make a short introduction. In the Roman times, ancient Rome, you know, those guys were pretty famous for building a lot of cool stuff. And now we have a couple of guys from Italy who are building the same cool stuff just on the platform. And they will be talking about the aqueduct project that they built. So I would like to invite IDECOM as our partner here, and Olivier, to join us on stage and show us the world wonders of Italy.
Cool, it works.
Yeah, you are. Yes, thank you very much, Olivier. Thank you all for inviting us to this event. I'm Alessandro Pedretti, civil engineer from IDECOM. Start working with IDECOM in 2018, more or less, as an engineering, structural engineering. Then I moved to a commercial and technical commercial position since we became Dassault Systèmes partner in 2020. Here with me there is Alessandro Tabarrini, that is the author of this this work we have done in these few months. So please introduce yourself.
Hi, hello everybody, and I'm graduated in architecture and specialized in management of built environment, and in IDECOM as 3D modeling and design specialist.
Perfect. Let's start with the agenda of today's session. Just a few words about who we are. So a brief introduction of IDECOM. Then we fastly move to the project scenario. That, as Robert said, it was not ancient, like you said, but it's an old water system infrastructure built in the beginning of the 19th. Then we will discover more about this, the scope of work, the customer challenges, because of our customer was, in this case, is a public authority that is in charge of the management of the maintenance activities and security of the infrastructure. Then we will discover the methodology we adopted for this project using 3D Experience platform. What was the preliminary stage for the construction of all the model and the processes we adopted, ending with the benefits of the entire project. As a little introduction, we prepare a video, but I want to be sure that the audio is okay. It's okay, but normally. Okay. Perfect. No problem. It's like a song as a background. So these are our. It's a collection of our main projects so far. This is a Taormina railway station we presented last year during this CATIA event, and we work we are the Dassault Systèmes partner, value-added reseller, so we work also in the facade market with our facade customers, and as you can see it here with infrastructure, linear infrastructure as bridges. This was a timber bridge near Lecco. This is a logistic warehouse and where we develop all the architectural and the structural and piping element in 3D experience. And this is another case for piping and oil and gas application. We use also 3D experience for site simulation, so and operation for construction phases. Then this is one of main blueprint that is the thanks to our strong background in the concrete fabric concrete. We're trying to develop some new advanced tool to 3D print elements for construction, structural elements. We also push the limit of 3D experience for the rendering point of view, trying to present to our customer their project. This is also a case in which we use 3D experience to collaborate with external design company from all over the world, in India based, then England and Italy. And this is one of the Dassault Systems project we are trying to reach with them for GIS data management and in general maintenance activities on our infrastructure. Sorry for the Italian, we have no time to translate it, but they are the key messages for 3D experience platform: collaboration, single source of truth, and digital twin for the world that we live in. Okay. Let's move to these slides. As I said before, we are a civil engineer company trying to invest our time and our effort, try to innovate our sector, infrastructure sector and AEC industry, leveraging on the Dassault Systèmes solution, innovative solution like 3D experience platform on cloud. Our services, we are more focused on structural design and integrated design, so it means we are in charge of the development for the architectural, structural and piping design for our customer. And since the last 3-4 years we used to work as or deliver also BIM services for our customer, trying to push to the experience platform as a common data environment. This is our timeline so far. We born in 2016 as a civil engineer company. We was always a user of 3D experience platform. Then thanks to our strong background in fiber reinforced concrete, in 2018 our R&D department start to study a new mixed design for concrete 3D printing of structural elements, trying to simulate the process of construction with robotic application in EMEA, and trying to simulate the mechanical behavior and chemical behavior using simul application. So that we decided to become in 2020 trying to sign a strategy partnership with Dassault Systèmes. And right now we try to provide virtual twin to our customers. Okay, let's deep dive to the project. As we said before, during the last 6 months we start developing a huge linear infrastructure, a water supply system, an aqueduct. This we cannot say any more. We cannot be more precise about the location because Italian government. These are restricted data. We cannot share about something about this for safety management activities. So this is simply a red line in the southern part of Italy. It's not enough, but 240 kilometers of infrastructure, and the scope of our of the authority was to trying to reconstruct a beam model of the entire infrastructure, taking into account the possibility to replicate all the damages to the infrastructure. This is an old infrastructure, so that there are a lot of failures due to landslides, because it crosses a lot of different type of terrains. So that they want to build up a beam model to handle such disease, and for other activities that are more connected to GIS data management and geological model management. Okay, we can skip to the next slide. The scope of the work, as I said before, for the customer is to ensure the safety of the infrastructure, because of it is a system of infrastructure that need to be always available, because if they shut down the flow of the water, more or less half of the south of Italy will be without water. So it's critical from this point of view to have all these maintenance activities and pay attention to all the damages along the infrastructure. The challenges of our customer when we met together for the first time was the incredible huge of information, all the manual drawings that in the time that has been replicated and as CAD DVG or the XF drawings, and reports with a lot of notes to represent the BIM model in one unique environment, because they try to use a lot of different software, but they can't handle such this large size scale del model, and also the ability to have one unique environment with GIS data and geological information. The other scope of the project is also to perform simulation analysis. We are trying to develop some tests about landslide simulation and that hits the infrastructure. So what is the methodology that drive us in these months? First of all, try to be connected to GIS data, and the customer use QGIS, that is an open source software to manage territorial information. So we start extracting data information about the infrastructure, that is a 2D plan, a 2D vector made of, it's a polyline made of vertices and edges. So we extract all this information, punctual information from QGIS, then we re-elaborate all the data in Excel, trying to relocate and using the exact coordinate of systems. And then we do a mass use of visual scripting and code script in order to automatize 3D model the entire infrastructure and to represent all the damages along the path. All these information are enclosed in our templates. Then with Alessandro, you will see how many templates and how many script and code we write down in order to build up fastly in just 3 months more or less all the infrastructure. So this will be the methodology we adopted. First of all, QGIS extraction and collaboration for data, then re-elaboration in Excel, Visual Script and code writing, and then using template for the model. The first steps we made with customer was just to be able to represent the entire aqueduct in a unique environment. So this was the first goals, and recreate everything from the scratch using all the documentation we had. So reports, 2D reports, and a lot of other historical information. After that, we were able to build up a BIM model of LOD B for Italian standards, and that is more or less LOD 100 and 200 for international standards. And we built up the entire aqueduct of 240 kilometers, geolocalized with a sample level of detail, like a unique section that has been extruded along all the path. But it was that the first step that guide us in the organization of the model, that give us the criteria to structure the model of the BIM model, and try identify the current BIM object and PLM object. So I will leave the stage to Alessandro, that will deep dive to the entire process we follow so far.
Thanks. Okay, so from a more technical point of view, we have 4 main stages of the work that are the alignment representation, the 3D modeling of all the templates and the elements, the typological elements present in the infrastructure, the failures and damages representation, also both with the geometrical and parametrical informations, and the building models such as classical BIM modeling. Okay, so speaking about alignment representation, we need to do an overview on the process adopted. So from QGIS, as explained by Alessandro, we have created an Excel matrix with X planimetrical coordinates, and we have integrated the planimetrical coordinates with altimetric values through the documents obtained by our customer. So to pass through from QGIS to the platform environment, we used a visual scripting design sequence. That is one of the main instruments that we can meet several times in our work. And in this case is the plani-altimetric 3D polyline of the infrastructure. After the first representation of the 3D polyline, that is subdivided into into site and the main traits of the entire pipeline. We have subdivided into minor traits, commonly due to the successive minor infrastructure that characterize the main aqueduct, that are, for example, galleries, channel bridge, siphons, and other elements. Also, in this case, we have created the target input for the modeling of punctual elements and buildings devoted to the service of the aqueduct. So, for the 3D modeling, we have collected a lot of data and informations from our customer, and there are a lot of heterogeneous data, drawings, reports. So we had a large study on all these data, on all these documents, and we have decided to represent and model starting from basic components that we can see, for example, in the corner, in the left corner of the screen. For example, for bridge, channel, galleries, and others. And we model initially the typological sections with parameters and geometrical information aligned to the documents that we received, and elaborating this information, this 2D information, with also in this case design sequences that automatically reproduce on a large site with important dimension, the geometrical features. It's important always to keep in mind that we are facing an infrastructure with a 240 kilometers length and composed by minor traits of also about 15-16 kilometers galleries, channel bridge of 500-600 meters. So an important part is the automation and generative design used to parameterize and model the elements. In this screen, in this slide, we can see on the left the 4 main elements that compose the infrastructure. So galleries, channel bridge, punctual and building elements as a service for the aqueduct, and siphons. The main instrument, the main tools we use to model is the template, the engineering template. So collecting all the parameters and typological information of all the elements that we find along the pipe, the aqueduct, in order to have only one single product that we can manage and set along the entire aqueduct to obtain different geometrical informations and features, and also to generate different parameters that we need to collect and that are important for the customer. So we can see in the right side of the slide the instantiation of several templates, so with channel bridge, galleries, and others. Okay, we can see some videos here. So, for example, this is the starting basic template of a gallery. So we have collected all the information of all the galleries that appear on the entire infrastructure in order to have only one single basic components that can be suitable for all the situations. So for example, here we can see different configurations type, such as with interventions inside the galleries. We can see also the management of the typological section, so with different shapes and dimensions, and all of these geometries can be seen and send parameters and attributes to the information management to the information management side of the work.
Bridge template. Non diventa grande. No. No. Sorry.
Okay, this is the template for channel bridge. So in this case, like happens with the galleries and tunnels, we have different geometrical and typological features involved that compose the entire infrastructure. So we collect all this information inside this basic template, and we can see in this case the possibility to manage all these typological informations inside the same template product. The target geometry input of these templates is always the 3D polyline modeled in the space, always geolocated and subdivided into minor traits. And we can see that collecting and studying the data of the entire infrastructure obtained from our customer, we are able to manage, in this case, step by step, all the infrastructure. This is the third main infrastructure element, that linear element that composes the infrastructure, that is a siphon. So an hydraulic infrastructure that follows a depression in the terrain that is usually longer than a depression that we can deal with a channel bridge. So in this case, also in this case, we have collected all the informations that characterize the siphons along the infrastructure, and we have also in this case a reading parameter for quantities and other informations on attributes and properties. This video shows the instantiation phase of the modeling activities. So after the creation of the templates that we have seen, that we have previously seen, we can see now an example of instantiation. So we can see a site, a general site, subdivided into minor traits, and we need to imagine that the terrain is very unpredictable and heterogeneous along the alignment. And for this reason, we have, with the fast succession, galleries and bridge. Also punctual elements and buildings that we will explain later. So about the damage and interventions representation, that was one of the main objective of our customer, so to map all the failures and damages that they have collected during the maintenance and inspection activities. We have elaborated them also in this case with the design sequence in order to deal with a large amount of data on with the large dimensions sites and infrastructure. So collecting the informations and documents like 2D drawings, reports, and Excel files. We have represented the geometries in a geolocated way through along the aqueduct, through also in this case design sequences that permits to model a large amount of data in automation way and generative design. So here we can see how the interventions and the failures representation works. So we have several parameters that send information to the design sequence to model geometries and to export attributes and properties that we need to collect and that are requested also by our customer. So in this case, we have created a design sequence that starts from a string parameter that works in this way. So modifying the string parameter, we are able to modify the subdivision of the aqueduct in minor traits, and to represent on these minor traits the interventions and the failures with a perfectly correspondent geometrical representation to the reality inspected from the customer. Also in this case, we are seeing the basic starting product, so the template product that we have instantiated on the entire infrastructure. For the first step of the modeling activities regards the building models. In this case, we have developed another template for the punctual elements in order to represent a lot of different buildings along the aqueduct, and also in this case we start with the QGIS to extract geolocated informations and to develop into the platform with design sequence that creates the target input geometries useful to instantiate with a recursive way with the component-based design. So in this case, the template is implemented with the component-based design, that is automatic template that use list and set parameters. So in this case, you can see in the left side of the slide the instantiation of different punctual elements and buildings with their own parameters and their own appearance, geometrical appearance. This is the starting template for buildings. So we have AKL script that manage the showing off of all the elements that are interrelated with geometries, the input geometries, that is the alignment of the aqueduct. And we have different types of elements also in this case, so like descending chamber, or well, simple well, or like in this case a symbolic representation of hydraulic towers. In this case, the objective is to represent and collect informations of all these elements that we need to geolocate into the BIM model, but maintaining a low level of detail, because we have, speaking about number, 300 elements all along the aqueduct. 100 galleries, 60, 70 channel bridge, 10 siphons. So we are dealing with an infrastructure that has a lot of minor traits and substructures. In this case, we have a more classical BIM modeling for buildings, for which we have drawings and more detailed table drawings. Okay, now I let the stage to Alessandro.
Thank you, Alessandro. The last two steps of our process are currently under development, and regards the GIS data implementation in 3D Experience platform, because they are trying to manipulate GIS information in order to review data and try to perform some geospatial analysis. So with the help of Dassault Systèmes, we are trying to test city referential application on the field for this application on one end, and on the other side we are also trying to replicate the geology scenario that the water supply system is intersecting underground. So with the help also again of Dassault Systèmes, we recreate the geology model of just more or less a few kilometers, maybe 20 kilometers more or less of the 15 kilometers of the aqueduct, in order to understand if the system is in collision with some lens failures or landslides, because the customer is also interested in to understand the possible future scenario of disease and damages on the infrastructure. So again, with the help of the Dassault Systèmes, we are trying to test solution, and we are trying to present them our solution for GIS data management and geology management. So what is the benefits in to close our presentation, that the customer is wondering that, and we are presenting to them is the ability, our ability to handle such a large scale project, and trying to give BIM data and GIS data in one 3D environment and context. And we try to push our ability to modeling such this element using a lot of automatized procedures, using their know-how and our know-how to support them the best. And of course, the collaboration, because everything is in one unique environment on cloud. So they will be able to access everywhere all the data they need to work with, and it's something that we are working day by day. So thank you.
Thank you, Idecom. I think Julius Caesar would be proud of you. Unfortunately, he didn't have 3DXP. Do we have some questions in the audience for the guys? Okay, one question finally. First question today. Please.
Yes, thank you very much for your presentation. At the beginning, there was shown a short video, and we saw some demonstration of capabilities of 4D planning.
4D planning, yes.
Yeah. Can you speak a bit about that?
Yes,
what did you did, and how did you use the 3D experience platform?
Yes, of course. Oh, sorry. Yes, we use the EMEA application for process extraction in order to build the construction scenario phases. So trying to connect the engineering items, so the design of the model from engineering point of view to manufacturing point of view, using different type of items and PLM object in 3D experience platform in order to simulate the site processes in order to build the construction. And we use them for a critical infrastructure in the northern part of Europe for the management of the new interlink in Sweden, and we use it for the planning of the construction of these new railways that is crossing the huge building in order to try to simulate all the goods movement around the sites. And then we use also for facade design, as you've seen before, and trying to collect all data, passing through the design phase to manufacturing phase also.
So you use it both for engineering and then for construction, or?
Yes, of course.
Yes, for both.
Both.
Okay, thanks a lot.
Thank you. Now, when we broke the Karin.
Thank you for the presentation. 3 months in the making?
Yes, more or less. We start working on beginning of July, so July, considering also holiday on August, more or less. This is
no, you're not working on holidays. So congrats for that. The last slide was about the benefits.
Yes.
In my experience, 20 years in the industry, a lot of clients have this vision of having this common data environment and 3D modeling. Have you been able to really measure the acceleration using engineering templates and generative design, and did the client really understand the power of the solutions you were using compared to what is out there on the market?
Yes, of course. The interest of customer is really high. They don't. They are excited to start working with the model, try to put their hands on it. And of course, this way of work, because of it was a 2 years old project, but we jump in at the end of the project, so the customer needs to build up all the models in just few months because the end of the project is half of November. But till now, so two years more or less are passed, and until July, they don't have anything in their hands to present to the board for the project they are investing on. So they are they were scary about they can't reach their goals, but fortunately we helped them a lot using our know-how and of course using templates and all automatism we developed to reach these goals. And of course customer understand the potentiality of the tools and the collaboration that can grow in between all the departments of the authority, because there are a lot of different departments connected, controlling the same elements, the same infrastructure.
So they will never start a new project without the 3D
Yes,
Experts platform?
I think so. Yes, of course.
Thank you, Corinne. Now, when we broke the ice, anyone else? Anyone else? Okay, then I'll call 20-minute break, so you can ask some questions aside. Thank you once again, guys.
Thanks.
20-minute break, and then we're back.
No, it's Robert. Okay, Robert and Xavier.
Yeah.
We will have a shorter break.
Yeah.
So in order to.
Could you just test if the audio works?
Yes, let's do it right now. Yeah. No. You know.
20 minuta će biti, da.
No, no, you can close it. Thanks.
Okay. So, small people. Yeah. Continuing with the presentations. So, Xavier.
Hello, I'm Xavier Bazy from Infrastructure, Energy and Materials industry, part of a solution team, and much more focusing on the engineering side. Robert, you want to present you?
And you know me.
So today I have the pleasure to make the presentation with Robert. This is to illustrate another kind of example. Okay, during all the day we have different kind of examples. So this is to illustrate another one. Just to say that through this example, in fact, we are. You will see there is a scenario from engineering to commissioning. It's not covering the full portfolio that we have. We have much more things, but as we have a shortened time to present, this is not presenting everything. Just for you to get in mind, in regards to the portfolio, a new time I will not be exhaustive, but as we are talking about governance, of course, we are thinking about project management, we are thinking about risk management, issue management, we are thinking about change management, configuration management, even making some life cycle assessment, very important for sustainability. Moving to engineering, this is something that we have started to see this morning with system engineering, where you will be able to define your system architecture, but also during the early phase being able to simulate your systems, so to validate your different systems and to make sure that you are still in line with the different requirements. Moving then to detailed design, so preliminary design, detailed design, covering all the different disciplines, structure, piping, HVAC, electrical. Then being able to move also, and that's additional also to engineering also, I would say also that we have all different kind of simulations, and we have also the control systems also that we can define and that we can test. After that, we have also the part which is the procurement, where we will be able also to do some, and we will see also another example on that during the presentation, very short, but about component management, standard component management, but we have also the capability to manage also the sourcing and the supplier management. We have also the part with fabrication, where we cover with the portfolio also the modular preparation and the modular fabrication, a topic that becomes very important for the industry. More and more people are looking for modularity. So this is something also that we are covering. Moving then after to construction, where inside construction, we will talk about 4D planning, which is a matter of simulating, but also making the planning for the construction in line with the engineering, but also covering the part of field execution. And just to say that, of course, here we are talking more about the engineering part until the commissioning, but keep in mind that, of course, all of this then can be reused as we talk about the virtual twin. All these informations, all this data, all what is available then can be reused and will be reused for maintenance and operation directly as everything would be ready. Robert?
I think that I finished presentation. Okay. Thank you, Xavier. This was a really deep insight from the industry. What you see here is the entire process that we as a company can provide to the certain customer on the end. This is the example, and all of these steps here are just a couple of videos that describe each step in making the change, making the green change, which means the certain customer who had a use case wanted to switch from the oil and gas back to the LNG and the hydrogen, and to see or to anticipate how that change can cost him, how much, and what are the steps that he needs to take in order to perform such change on the end. It's important to note that for this specific customer, we did a deal with all the brands. So this is not just the CATIA, although I will present the CATIA part. So we have NetVibes here in picking the OEMs, so the suppliers, the subcontractors. We have Anovia, of course. We have Simulia in making the simulation because we are now dealing with explosive materials, more or less. So LNG, hydrogen. We need to change the equipment. We need to purchase the equipment. We need to make the simulations. So Daimola, Control Build, MBAC, the entire or the big bunch of the brands that we have within the company is now on this presentation. A lot of teams make the effort to make this work. It was presented on the customer on the end by a couple of persons, and hopefully it was successful. The main idea is, as I said, switching to the green energy, switching from oil and gas tank to the hydrogen and the LNG. That means you need to change all the systems within. You need to change the pipes, you need to control the valves, you need to have the bigger exchange of the information and the control of the information. So for the start, we will start with... you don't have the pad working. Oh, I need the mouse. Yeah, boy. Okay. Okay, next. So with the small mouse, it works. Yes. On the business government side, so we need to set up the project. Thank you very much. That's why you're my manager. We need to set the project. We need to pick from where we're going to get all the suppliers, from where the equipment is going to come. The picked equipment, so the one that we simulate, we're going to purchase on the end. And hopefully this is the PLM analytics on the end that we can see the cost, the time, and all the differences. We can make the analysis of getting that equipment on our site. And of course, all the tasks that are related of purchasing that equipment. Now when I have the mouse, now it's better. With the MBAC, we can make the simulations and to anticipate. So with the ISO 15288, which is basically describing on how a system of systems work when the human is interacting. We can make a certain simulations based on the PFDs, BFDs, PNIDs, or make our own assumptions on the system to see how the system will behave later on. On the beginning of the project, we have a lot of requirements that are going to be pushed inside. The platform allows us to push all of those requirements from the specific documents, either the technical specification or equipment specification, or just some email from the supplier that we received yesterday. So we can push them on the platform, and we can reuse them later on to make the simulation, to make BFD, PFD, PNID, 3D, and changing those requirements, we can basically drive our design, what we're going to see later on. Since each of the equipment have its own set of the attributes, we can deal with a lot of them. They can be engineering attributes related to the specific system, like in this case, it's going to be the pressure and the temperature, operating pressure, operating temperature. And those can be used also to make the change in the RFLP. But also those can be used to make the simulation in the early stage so that we can anticipate what's going to happen later on our system. In the specific case, those requirements are pushed on the platform. We can play with them, we can extract them, and we can change them. So each change, of course, is recorded, and each change has an impact on the next steps of the process. In the specific case, we are changing the pressure because now dealing with oil and gas, dealing with liquid natural gas, dealing with the hydrogen, so we are increasing the risk of the system. We are increasing the pressure, reducing the temperature. That's going to have the impact on the entire system. So what happens if we increase, for example, just the pressure, decrease just the temperature, or if we combine both in the certain simulation? We can make a simulation based on that, and with those outputs, we can push them as additional requirements on the software that can, again, later on impact our design. So not doing the physical system here, making some simulations and breaking the equipment and losing a lot of money. With MBSE, we can anticipate that.
Early design validation.
That's why we have industry here. Okay. On the mechanical design validation, so we need to purchase of all of that equipment. If that equipment is manufactured, so if it's one of a kind, maybe we need to make some simulations. In this case, it was Simulia, FEM and CFD analysis, to see how the equipment will behave in those new conditions. So again, Simulia will allow us to see all of that behavior in the real time. And later on, this can be one of the requirements that we can push. Okay, we picked this and this equipment because of this and this result. Just to skip it, it's not that I don't like Simulia, but the main part is on the engineering side. So what do we have here? We have here the system that's already been designed before. That has a certain set of requirements already connected with the logical and with the physical. So in this PNID here, we're going to change the blowdown line. We're not going to change the entire line step by step, but just by increasing the operating pressure, we can see, because of the connected systems with the update, how that change reflects the entire system, because all the parts within the RFLP are connected. So, changing the pressure, 1400 psi, and updating the entire system. There was a change in the nominal size, there was a change on the type of the valve. Since the logical is connected to the physical, there was also a change on the physical side. And that can be, of course, traced with system traceability that we're going to see later on. So if you have the case, you can see all the steps that have changed just by changing one requirement. And of course, there can be thousands of requirements on the end, but we can trace all of those requirements simultaneously. The list from the equipment, in this case, the valve that we see is the exact valve that was simulated before, purchased from the specific OEM and pushed now here in the new model. On the 3D side, because of the checks and the rules that we have on the platform, we can see how that traceability looks like when we have the 3D. So each engineer can run the rules and checks and see if they are compliant, if the 3D model is compliant with 2D that was done before. In this case, since we changed the requirement, it changed the nominal size of the pipe, it changed the type of the valve. With the check, now we have the update that there is a change on the 3D. And just again, by updating, there are certain steps behind that updating, we can see the change in the 3D. And that's it. On the end, the decision, when we finally define the 3D model will be up to the deliverables. So the drawings are updated, the equipment list is updated, and maybe some equipment specification and the purchase order for the OEMs and the supplier is updated too. And if we talk about the equipment, just complementing what Xavier said before, all of that you saw that was pushed on the 3D exists in a certain place on the platform. Okay, it's the catalogs that we gather from the OEMs and the suppliers, but through the procurement phase, we can go to the 3DXP market where we can use those models that are pushed there by the OEMs. So if there is some OEM or the supplier listening us or here, feel free to provide all of your inventory or on the platform. We can reuse that. We can use that for other vendors, for the other owner-operators. They can access the information on the platform. They can decide on the platform whether they're going to use that or not. So all the technical specifications and everything related to the equipment is already there. So let's say that those are libraries, general libraries from the real manufacturers that can replace in a certain way catalogs that we already have on the 3D side. And the information of purchasing the specific valve that was used through the procurement intelligence goes directly to the supplier, contacting the supplier and getting the valve on site. Of course, Dassault is not paying for this valve, so you need to pay for the valve on the end. Getting back on the planning, because we need to build it on the end with the EMEA. I'm just going to quickly go through it. So all the steps that we did before, changing that on the 3D side needs to be physically changed on site. So how we can make something work, because if we build it in the 3D, it doesn't always need to think that we can build it on the end. Just pushing in a couple of cranes, making a certain steps or the processes that can be delivered as the packages on the end. We can also replace the old equipment and push in the new one, which is generated before. Of course, within the planning structure, this can be pushed in the Gantt charts so that you get all the steps separated with the EMEA. But this is a completely different picture. Resource optimization, I will skip that a bit. We can discuss it because we are a bit out of time. But the digital execution is something worth mentioning, so that all the steps that we planned before, as of through the platform, they can be pushed to the specific persons for the execution. As we had different users on the 2D, on the 3D, the designers, the architects for the electrical, for the fluidic, for the HVAC. Of course, we have different ones on site. So each one of them can have a certain package of the 3D that we built through the digital twin. And of course, a bit more details on it, because there is a safety first rule on how to install those stuff on site. So basically, the entire life cycle of having the idea on the paper or on the platform, pushing it on the platform with certain stakeholders, spreading the idea to the suppliers, to the subcontractors, working on the idea during the concept basic detail design phase, and finally pushing the deliverables to the people who are involved within the project. That can be done on the platform, again, repeating the platform. Key target metrics in this case for each one of the steps were evaluated by the customer. You can see the results down below. So again, since there is a single source of truth, we can spread or evangelize all of the brands within the platform stuff, so that all of the information that we push in stays in. I know that we went pretty quick through it, so if there are any additional questions, we can have a lunch break or a coffee break later on. Feel free to get in touch with us or within the team who worked on it, and that's it.
Thank you. That's it. Digital continuity.
Yeah.
No question? No question? Okay, so let's continue. Thank you very much, Robert and Xavier. Let's continue now. Please welcome Björn from European Spallation Source from Sweden. He will talk about how to manage with 3D Experience platform information and data from early design phase till operations and maintenance. Thank you.
Thank you very much. So the European Spallation Source. Now let's see if we have audio. Normally. So we'll just have a brief overview of what the European Spallation Source is first, and then we will see how we actually at European Spallation Source manage all our engineering data, multidiscipline, throughout the full life cycle from early phase design through to installation commissioning, but also over into the operations and maintenance phase. So, nice video, but how does it really work? The entire facility is comparable to a huge microscope. So, when you did biology class or when you as a kid looked into the microscope, you know, the black ones, when you had a flashlight, shining light to a lens or a mirror in order to see whatever you were looking at through the microscope. It works similarly, but we're not using light. We're using neutrons. And when you do that, you can actually examine things in our instrument halls, in our instruments, down to the atomic level. So the process starts at the ion source at the left there, where we actually produce protons, and then we accelerate those protons up to about 96% of the speed of light in a 650 meter long linear accelerator until those protons hit a target. And there, neutrons are spallated, so that's where a spallation occurs. So all those neutrons, they're then slowed down, focused, and sent down beamlines, is what we call them, to individual instruments. instruments, and those are the green dots that you see there. There are differing length for them, which gives them different characteristica, which means that you can perform different kinds of analysis for different kinds of applications. The timeline for the European Spallation source is that we started construction in 2014. In 2019, we started initial operations phase, meaning that a lot of our infrastructure systems are already up and running. We have now, for instance, commissioned some of the cryogenic cooling systems. All the electrical and stuff are ready, and we are installing large portions of the accelerator. Today, 2023, we are on our way to first science in 2027. So, information management. How do we manage all the information needed to build a facility like the European Spallation source? If we examine the ESS responsibility from a life cycle perspective, if you have a normal life cycle through design, engineering, procurement, construction, commissioning, operations and maintenance, and decommissioning, ESS is responsible for the engineering, procurement, construction, installation, and commissioning of the facility. So yeah, we are an EPC. But we also design some of the products that are used within the facility because they simply weren't invented yet when we started. So we're also a product company, and we manufacture those product designs. And we're an EPC, which means that we have to deal with all kinds of other manufacturers in the EPC supply chain. But ESS is also responsible for the operations and maintenance of the facility, and ultimately its decommissioning. So we have to cater for all the needs of an operator. So within one organization, the European Spallation Source Organization, we have to cater for the entire value chain that you see in normal industry, for instance in energy, where you might have an operator. It could be Shell, it could be Exxon, that contracts an EPC to get something built, which then contracts a lot of product companies and manage all the information and hand it over to the operator after commissioning. We need to deal with all of that internally. So if we look at the information needs that needs to be managed to build a facility like the European Spallation source, up until commissioning, we need a functional breakdown structure, so normally referred to as a master tag structure. That is the structure that breaks down systems to subsystems into functions down to the lowest level, down to the lowest maintainable level of a system, or if it has a safety function. And this is a huge structure. It's multidiscipline. It entails plant and process, electrical, mechanical, and even infrastructure, and civil and structural. Currently at ESS, this structure is comprised of 250,000 tags, but there will be a lot more. It's not uncommon, like CERN, for instance, which we have widespread collaboration with. That's 1.5 million tags. It also makes sense to use a location structure. You want to know where all your functions are, not only system, subsystem, but also where is stuff. So is cabling spanning multiple locations, or are they residing within a location? And then you have the parts management, the engineering, bill of material, the product designs. In our case, we have to cater for complex mechanical CAD product designs, as well as just single parts catalogs that we procure from someone. It also makes sense to, as was mentioned in the previous presentation, to have some control of the procurement aspect and the supply aspect. How are things supplied to the project, to the site? And when stuff arrives, so physical products, meaning individuals that you can touch that has a serial number. When do they arrive? Does it fit with the project execution plan? Personally, I've been working with a lot of EPCs and a lot of operators. I've never ever seen a project installation plan go exactly according to plan. So you need to have a plan for where to intermittently store stuff until it is ready for installation. And if you do that, you can be quite sure that if you had 10 valves and a P&ID, one of them was in a safety zone, so it has special certificates, and you don't have control of where it's stored in the warehouse, you can be sure that that safety classed valve is going to be used in an unsafety classed area. Meaning that when you actually start to install the rest of them and in the safety classed area, you can't find it. Meaning that you either have to dismantle the installation you did previously or you have to ask the manufacturer for a new one, which is very costly. So all of these information structures, it looks very well. It's quite frankly, it looks quite siloed. But the importance is that these objects, tag, part, asset, they need to be interconnected. Then you start to reveal context. What context is the part used in? What context is the asset, installed asset, used in? And in the middle of the circle here, you see something called reference data, which I will come back to. But wouldn't it be beautiful if plant and process design, the tag structuring, would use the same nomenclature, the same class detecting instrument as product design would? And ultimately, when you receive an asset, that what's stated on the asset is the exact same information, the same attributes, the same classes, meaning that you can compare, not only as a human, but also do that machine-wise. So we'll touch a bit on what we have done in that area. Because during operations and maintenance, what we really want to do is to operate and maintain the facility so that we have the best possible uptime for neutron production. We're a neutron factory. And we have some very interesting requirements on us. One of them is that we need to be operating, what was it, 4,000, I think it was like, no, 40,000 hours a year, and with a 96% uptime requirement. And we cannot do that unless we move into preventive maintenance and also predictive maintenance. Meaning that we need to harvest data from our control systems, from all the sensors that we have on equipment, tie that to how the assets are calibrated, but that needs to be tied to what were the functional requirements for that system. What is that asset doing to fulfill the functional requirements of the system in a best possible way? So what does this actually look like at ESS? So we needed to put in place an information model that was able to support the entire life cycle. And we started that work in 2013. And here, Peter Rådal and Magnus Teklin, who is also with me today, were very early in actually defining that our ways of working needs to be backed up by our information structures. So we needed to have an information model. And then how we are going to work with those throughout the entire life cycle of the facility. So looking into our tag structure, this is actually an OVIA. It has a different GUI overlay, but all the data, all engineering data across all disciplines, whether it's plant and process, electrical, civil or structural or mechanical design, it's all consolidated within the Innovia platform. So this view gives a single entry to all facility information. So the actual tag structure itself, what it looks like, 250,000 tags at the moment. You can dive deeply into more the details of the tag information. So for this radio frequency quadrupole support system, which is a mechanical support system, you can go in and see attribute information, you can see lifecycle information, you can see documentation associated. And by clicking a paperclip, you see all tags related to, all documents related to that tag. So for instance, for this cavity system, you have immediate access to all requirements, specifications, test reports, drawing files, etc. And the little green icon just says that they are released in the context of the system. But I just mentioned something about reference data, and we'll get back to that. All systems, all tags, they are classed according to ISO 50926, which was a standard we started to use for reference data. So all tags have attributes and unit of measures defined. So we are rigged to run solely on data. However, we still have to cater for the fact that a lot of our industry is still document oriented. So we need to cater for the release process and the connection for specifications documentation as well. And we actually have our own team, technical content management, who takes information that we get from our sub-suppliers and makes it into metadata for use in operations and maintenance. Looking at this little icon, it gives actually a reference to our EPL, our ESS plant layout. And that's the 3D master model of the entire ESS facility, which is managed in CATIA. And in a second, we will look into how that actually looks in CATIA. But what's different with ESS compared with a lot of our other companies is that we master the 3D master model in CATIA, but we also do product design within CATIA. So we have to cater for product lifecycle management and design, and plant lifecycle management and design within the same CATIA platform. And to do that, we'd have to do some small tweaks, but we have made it work with CATIA. And if I go into one specific tag in the FPS, which is the functional breakdown structure, the CATIA objects, they define the spatial boundaries of each tag. So by looking into that one, this is one of the cryo modules that the proton accelerator is comprised of. So by going to the 3D markup app, so bear in mind that this is through the web interface. Then it will load the 3D spatial boundaries of the cryo module. And this is not a product design. This is instantiation. It is one tag out of the 22 tags. So of course, as you go in, you get more details, but the actual product design is extremely more detailed than this. So we have taken away things that are not important seen from a facility or a functional breakdown structure point of view. Is the big screen flickering as well, or is it just this one? Okay. So that was one small tag within the linear accelerator, which you see there in the brownish and purple color. But what about the entire ESS plant layout, the entire model? So as I mentioned, all space allocations refer to tags, and they're tied back into this huge model. And we can view from multiple disciplines. So let's see what that actually looks like. So we're going to look into a portion of the target where the spallation occurs. And we're also going to load some of the laser scans into it in one model. so that we can have an overview of both the as designed and also the as built, because we do laser scanning and import as well. So here is the target drive unit. And what you see around it is actually a laser scan of the shielding. And this goes for the entire facility. But of course, you cannot load all the details of the entire model every time. So you do segments of it. We have a virtual reality room where we actually load very large portions of it, which we use both for training, also for rescue processes, so fire and rescue, etc. Moving back to the functional breakdown structure, the full tag is in alignment with the tagging standard ISO 81346. And there's a description of each tag, and here you can see the reference data class used. So if you see at the bottom there, you see flow meter. Of course, we've got a lot of flow meters across ESS. All of them refers to this class, which gives them a set of attributes and unit of measures for each tag. The same on the part side. So if I have 10 flow meters referring to one part, that means that I have the need of 10 in my project or in the system, and I can realize it by one part or one product design. So quantity 10. So you can automate the material takeoff process. There's a status, it's whether it's released or approved or in preliminary, and I'll get back to that a little bit because that's quite different from traditional product lifecycle management. And there is also a reference to the part that can be used to realize the need for the tag. Sometimes you see multiple ones, like for the flow meters. That just means that you can select two different parts to satisfy the same functional need. So from an engineering point of view, it doesn't really matter which one you choose. For engineering procurement, you can be quite certain that they will have a preference, whether that is for reliability from the supplier or quality or whatever. You have an entry point to the tag's location, so in the location structure, and entry point to the tag's installed asset. Meaning, again, that you have traceability from the initial tag requirement through the part to the actual installed asset and how it's calibrated, which is commonly referred to as a digital thread. The functional breakdown structure versus product design, engineering bill of material, and here's where the difference is between standard product lifecycle management and plant or facility lifecycle management, because the tag structure is released in a top-down fashion. It doesn't make sense to detail your P&IDs, your piping and instrumentation diagrams, unless the process flow has been agreed upon. So at ESS, we actually have made an OVIA work top-down for the FBS and bottom-up, as usual, for the engineering bill of material. The ESS plant layout, the spatial integration part, we use for clash analysis of revised design models. So here you see a newly revised model that when we put it into our ESS plant layout, which is multidiscipline, we clearly see that there is a clash with the collector here. So it's useful for that. But we also use it for as-designed multidiscipline view with as-built comparison. So what you see here in those two images is the as-designed model on the left side and a laser scan. It's not an image, by the way. It's a laser scan on the right-hand side. And here we can see that the portion that's in red there, that the handle of that valve is actually in a wrong direction, which will pose a problem later on when the other disciplines have installed their part. So very useful to detect issues early. We had one very, very serious example all the way back from civil and structural, because since we're classed as a, actually we're more or less classed like a nuclear facility. And we need to have huge pylons going down all the way to the bedrock. And in the south of Sweden, that means 20 meters. So there are huge steel pylons, and there are concrete and steel reinforced pylons going away all the way down to bedrock. But one of those have been placed in the wrong location, and they stick up a little bit from the Earth's surface. But no one really noticed until our survey and alignment team, which does laser scans continuously, brought that into the design model and saw that, wait a minute, if we let this slide, then we're not going to be able to install some very critical parts of the facility, which would mean disaster for the project. It cost quite a few million to actually redo it, but it would have cost exponentially more if that hadn't been detected and we had gone on with the project. A few other images. This is still, it's not product design. It is the big 3D model of ESS. The first couple of meters of the linear accelerator. And the bottom picture, you see some more going a little bit closer, seeing some more details of the first 2 meters of the accelerator. And here's another example where you take actually just a laser scan. It hasn't really been cleaned, but you just put it on top of the as designed, and you can immediately see whether they actually fit, if there is a match towards the as designed. So the curvature of that piping is quite good, very good in fact. And you can also see that some of the other disciplines, they haven't started yet, which is fine. Our location structure, it's built pretty much the same way as the functional breakdown structure, but this time it represents physical locations. So you can, I don't know, can you actually read some of it? So in this case, the accelerator buildings is broken down from the site to area to buildings. So the gallery building is then divided into different levels. So level 100 just means it's ground level. And then we have the gallery technical area, which is a huge room. And to make it a little bit more easier to work with, we have then divided the rooms into cells. So if I click here for the test stand 2 area, I will immediately see all the tags, all the functional tags that reside within that area. And of course, I can go the other way around and see my cryogenic cooling system. Where is it? Well, it's exactly in this area. So that helps a lot for installation. It helps for commissioning. It helps for operations and maintenance. If we examine the product design areas, this is an engineer. It's also a multidiscipline. Engineering bill of material, but this time only for the product aspect. So this is one of our designs, the moderator reflector plug. It's a critical piece of equipment within the facility. Its engineering bill of material is about 230 parts, and it is released in a top-down fashion, as you would expect an engineering bill of material to be. And on the right-hand side, you see also the 3D markup app, but the entire CAD design of the moderator reflector plug. Did you have a question, Peter, or was it? Sorry, did I say top down? Oh, sorry, no. Bottom up for product designs. Thank you. And again, yeah, top down, functional breakdown structure, bottom up, engineering bill of material. And this is quite unique. I've been working with quite a few EPCs and big product companies in capital facilities industries. And this is actually the first time I've seen this dynamic done from engineering. And it has helped us a lot. So there is a change order governing any release in the functional breakdown structure, but it governs it top down, and all documentation needs to be released before the tag is released. So now we've covered pretty much everything up until procurement. But then when we actually get the assets to site, then we manage it in our enterprise asset management system. But all the information from Enovia is available in the enterprise asset management system. So the entire tag structure, access to all the data, access to all the documentation, both on the tag side, but also on the location side, is available for operations and maintenance. So if we examine one asset, in this case, a crane, 15-ton crane in the loading hall, then we will see, they refer to it as position, but it's the tag. That comes from Enovia, the location comes from Enovia, but then you can see that the asset, it is installed in the upper right corner, and it is also linked to the manufacturer and the manufacturer's serial number. And the little tab you see where it's written CHESS documents, that's the access runtime to all the data from Enovia, which we happen to call CHESS, Collaboration Home of ESS. I never really figured out what came first. Was it the abbreviation or... And of course, in the enterprise asset management system, that's where we actually execute all our work orders. So this is just a screen from one of the tablets that they use in maintenance to execute work orders. But here we dress the information together with the tag information, the assets, with our preventive maintenance scheduling, work order execution, lockout, tagout procedures, and who's doing what where, and what sort of certification they do have. So as reference data, used by tags, by parts, and by assets, we used ISO 15926 Part 4 as a starting point. But what we discovered was that, yeah, we could import the entire standard into Enovia using Library Central. We got 3,000 attributes from the standard, which was great. The only problem was that those attributes were not assigned to the classes. So what we needed to do was to form a master reference data group across ESS from all disciplines, different engineering disciplines, and operations and maintenance, to see from a European Spallation source aspect what data do we need on each and every class, because then we can reuse that for everything. And we've been doing that since 2015, and it is now in a pretty good shape. And what ESS did back then is pretty much the same as what you find in CIFAS today, so Capital Facilities Information Handover Specification. So the later releases of that specification gives you pretty much the same as what we've built with ISO 15926. But from our perspective, 2014-15, we couldn't really wait. We needed to have master data that was workable for us now. But I've seen Dassault is looking into CIFAS, member of CIFAS, and we're also monitoring it to see if we can migrate or if we should migrate towards it. But the jury is still out on that one. But using classes from Library Central and connected data, of course, then gives us traceability the other way around as well. So I can go to a class, in this case, a flow meter, and I can see every single object that's using that class. All tags, all parts, and all assets in the facility. And this is what it actually looks like. So if a tag has been created that is a pump or any subclass of pump, those are the defined attributes at ESS that you see on the tag. or on the part, or on the asset in EAM. Same for process instrument or detecting element. And it allows us to run on data. Because if that's in a data sheet in Excel or PDF, and you have PDF on the tag and on the asset, you need to have a person looking at these. And is the asset actually calibrated satisfactorily towards the tag requirements, the design requirements of this system? If it's data, yeah, it becomes a lot easier for a human, but it's also machine readable, which means that all manners of new possibilities are coming forth. So it really enables a true digital twin for operations. When you can connect data from your control systems to the assets, reading the design parameters, and actually making data into knowledge about how the facility actually works and responds. A few words towards the end about the different systems and integrations we've got in place at European Spallation Source. So Enovia, or 3D Experience, is the one place where we consolidate all engineering data. So from plant design, Aviva P&ID, Aviva diagram, and E-plan for electrical. Product design, CATIA for mechanical product design. We use E-plan there as well. And for spatial integration and simulation and analysis, there we have the large ESS plant layout, and we use some other systems as well for simulation. And the entire civil and structural, so the entire BIM model, both from Revit but also from Tekla, all consolidated within 3D Experience and in the ESS plant layout. Which means that data from Aviva diagrams, E3D or 3D, electrical, E-plan for the facility electrical infrastructure, CATIA for all the product design, CATIA for absolutely everything with respect to spatial boundaries of the tag structure. And here is a little bit of a different use case, but it's still the ESS plant layout. But this is how we use it in our VR room. The video is from the first couple of meters of the accelerator. Quality so-so. I had to re-render it from a 360 video that we use with VR goggles. But this is the same data. It's just being used in a different way. So when you have data this way, you can use it for any number of different use cases. And it's not flickering in our VR room. And then one of the most important integrations that we have. So how do we utilize all of this engineering and design data over into operations and maintenance? So the EAM system that we use used to be Infor EAM, but they got bought by Hexagon, so now it's Hexagon EAM. But there is a very tight integration and coupling. So all design data is readily available from the enterprise asset management system as well. And all the integration that you've seen, they are being enabled by the reference data. Because when you integrate system A to system B and you agree on the data contract on everything between them, it becomes very, very easy to integrate. If you have to have a mapping, huge mapping file in an integration, in an enterprise service bus or whatever, that you have to learn what it's called in system A versus system B, you end up in a mess of point-to-point integrations. But whereas if you can agree on a common data contract, it becomes easier to integrate I really liked one of the slides from DS here where it said interoperability, because that's exactly what it is. It creates interoperability not only between software, but also between stakeholders in the supply chain and in the life cycle. And that is pretty much what I would like to present. Any questions?
Yes. Yes, thank you very much. At some point, you mentioned that you have taken away the details.
Yeah.
And I wanted to know what was the basic process. How do you identify what can or should be removed, and how you manage the configuration management between the asset without the detail and the asset with the detail?
So that's true. So for let's take it from a product design, which is extremely detailed. Now, when we want to use that and serialize it, so for instance, we would have a product design that is very, very complex for a cryo module. In the accelerator, we got 22 of them. Seen from an operations maintenance perspective, or even manufacturing perspective, because we don't manufacture those ourselves, we don't need that level of detail. What we're mostly interested in is in the spatial boundaries of the cryo module and its interfaces towards electrical, cryogenic cooling, etc. So what we've done is to actually, we scrape them from detail of the internals, but we leave some internals, not all, but some, which is what you saw in the 3D markup. And we use actually a tool that has been developed by a value-added reseller of Dassault to actually scrape the levels of details that we don't need. We would really like to have some sort of a better method or process of doing it. So we have our own team, spatial integration team, who actually makes sure that the ESS plant layout model is fit for purpose from that perspective, not necessarily from product engineering perspective, so that we don't have too much detail in the entire ESS plant layout. Because if we had 22 replications of the product design of a cryo module, you wouldn't be able to visualize it because it would just be too heavy. But I must say we're impressed by the level of that CATIA is able to manage the entire EPL, because there is an enormous amount of data in there. But if you structure it smart, you can really put in a lot of data. So the entire EPL, all tags have functional references, and they're controlled, the space is controlled by the CATIA EPL.
So, if I understand well, every time you make a modification to the engineering reference design, you need to redo the extraction on simplification?
That's done in the authoring tools. So that could be Viva E3D, or it could be CATIA for mechanical design. But we actually align the EPL with where they are in their design phase every single night. So it's updated every single night, or on request. So if they need it, they get it within the hour. So there is a type.
It's not replication. It's using the same data all the time. If you update it, detail one, this one will become updated.
Yeah, that's true. But for the product designs, we serialize them, so they become their own instances based on the product design. Any other questions?
Yes, classic.
Yeah, my questions are not really questions, right? Very impressive. I think the fact that you own the whole life cycle was the enabler for the vision and the motivation also for having this understanding of structuring the data for the operation and maintenance phase. You've been long collaborators, strategic partner of Dassault Systèmes. What's the next phase for the people here today? What's the next phase? What do you see as being the next innovation development you want to push with Dassault Systèmes for the phase you're starting operation and maintenance? And a second question, how do you see your stakeholders or collaborators in terms of the international project teams that will come to the facility to do their project? How do you see them at some point maybe using your virtual twin to be better prepared and more efficient on the execution of the project when they arrive on the facility?
Yeah, so to answer the first part first, yes, since we own the entire life cycle, it offers opportunity. And I must say and commend both Peter Rodal as chief engineer at ESS, owning both the design way of working and the maintain way of working, and Magnus Teklin, who is heading the engineering management team. They were very early in identifying the fact that we need to have such an information model in place all the way back in 2013. That model that I showed has not really changed because it didn't have to. But we have adapted tools, we have adapted processes around it as we've gone. So that helps. But on the other hand, industry is trying to struggle with the exact same thing. But there is the operator who actually sets the requirement on the EPCs. Some of them are trying to do it, but we have the luxury of actually what we do in engineering. We cannot blame Technip. We cannot blame someone else. It's our own fault when we hand the information over to ourselves in operations and maintenance. So we needed to figure out a way so that it works all the way. To the second question, the next step is, of course, yeah, we have structural data. The data is interconnected. It's machine readable. It's machine readable. So the next step is to tie in all the control systems. We have multiple control systems. So we have one extremely advanced control system for actually controlling the proton accelerator. But we have industrial SCADA systems that also need to talk to, we need to harvest data from. We have to tie all of that data to our installed assets. And of course, that will tell us what happens to the actual asset. But it's not until you see what the asset was actually intended to do at ESS in the form of the tag requirement that we know whether the system is operating well, good, or bad, or if there is something happening with the asset that we have experience of. When this asset actually behaves like this, it normally is 10 hours before we have a catastrophic failure of that asset. So learning. And then we're into the digital twin for operations realm, which is extremely powerful, but it means you have to tie sensor data to asset calibration to what was the asset intended to do in the first place. All of that has to come full circle. So that's a part of the next step. And the step after that is to utilize predictive maintenance. Because again, we have an uptime requirement at 96% when we say we're in operation. Because we don't want to have 3,000 scientists who have booked experiments in our facility and we can't produce the neutrons that they need. That would be catastrophic. So that would be the next steps. And yeah, we have strategies, and yeah, we are moving in that direction. But it's still pretty early. Was that answer? Anyone else?
Any other questions? No? Thank you once again. We will definitely discuss that Viva part later on.
I'm counting on it.
Yeah. Okay, so far we heard about the greenfield. We started a little bit about 3D scanning. But what happens if you have engineering company that is working with your solution but it's also developing parts of your solution. So it's doing our job. The next presenter will answer, I hope, all of those questions. Aitak from Croatia, our partner in crime. Nikolina and Marin, please join us on stage.
Hello, hello to all of you. What can I say after this great introduction, except thank you. Thank you for inviting us, Robert and Olivier. So my name is Nikolina Rebic. I'm coming from ITAC company. I'm a business development manager for the last 10 years in ITAC and for the last 5 years acting as a member of ITAC board. Today's topic is basically all about the change, transition, which leads to sustainable and smart design. The main presenter is my colleague Marin, but I will steal a few minutes and just introduce you a little bit with the activities of our company, ITAC. After that, Marin will talk about reverse engineering, digital twin, and he will also show you some examples of 3D scanning activities. So ITAC, as Robert mentioned, is a Croatian-based company. We have 5 offices in 4 different countries. 2 offices are located in Croatia, headquarters in Rijeka, additional office in our main capital, Zagreb. We also have 3 companies, one in the ITAC GmbH in Germany, the second one in the Netherlands, and the third one in France. We have more than 20 years of experience, currently employing more than 130 employees, which successfully done more than 300 engineering projects, which are coming from the 4 main pillars of our activities. The first pillar is related to CAD and PLM services. What we are doing there, so basically we are helping our clients to implement advanced CAD and PLM solutions. Basically we are focused only on Dassault Systèmes products. The second pillar is R&D activities. So we are constantly developing applications on top of CATIA and on top of 3D experience. Marin will also talk about this later. Within our 3D technology department, we are also actively involved in VR technology and 3D laser scanning technologies for the purpose of reverse engineering or quality control or retrofit in order to get as-built documentation. But at the very beginning, we started as a marine engineering company. We were focused on the passenger segments of the ships, doing some awesome projects, mostly mega cruisers, yachts, and naval ships. And currently, we are engaged in 2 very huge projects in naval industry. One is for the German Navy, and the second one is for the Dutch and Belgian Navy, where we managed to incorporate all the services that we'll show today. So basically, we started with the implementation of the 3D experience up to R&D services, 3D scanning, and then at the end in the engineering. So all our projects has one thing in common. All have been done using 3D experience platform or the Dassault Systèmes products. We have very extensive history with the Dassault Systèmes. Even if you read our name in the backward, it says CATIA. Currently, we are a system integrator partner. And what are we doing? We are bringing value to our clients by helping them to implement a 3D experience platform based on their requirements, based on their needs, and based on their business processes. The brands that we are currently supporting are related to CATIA, EMEA, EMEA, and SolidWorks, but are not limited only to that. And our clients are coming from different industries, industrial equipment, process industry, marine and offshore, as I mentioned, aerospace, as well as infrastructure, energy, and materials. And our intention in the future is also to spread to other industries, other complementary industries. Currently, we have like 60 dedicated engineers. All of them have a background in engineering, of course, but all of them are also power users for the different segments of 3D Experience platform, either CATIA, EMEA, or EMEA. We have a very large training center we provide training support for our clients, for the user training, admin trainings, but we are also performing platform support in terms of platform installation services, data setup, maintenance activities, and so on. So basically, turnkey solution for the 3D Experience platform. So this is in short line about our company, and I will leave the floor to my colleague for the technical aspects of the presentation. Thank you.
Thank you. Well, now I will talk about technical aspect. I'm using CATIA since 2006, and I started with CATIA before. As engineer, as a consultant, and now I'm leading our consultancy group, so I'm no longer working directly with CATIA, but with people who is implementing it. Beside everything that Nicolina already mentioned, we have our product development part of the team in solutions. So we have several products that was already made based on inquiry of our customers. So one of them is automation with importing mass data. So if something can be done in Excel and then import into 3D Experience and create it. So let's say something like maybe Idecom was talking about, or if you have needs to get lots of logical items just in the tree, it can be done instead of a few days entering with Excel, and just in few seconds can be created into 3D Experience. One of our products was also ASD, smart drawings, now called multidiscipline drafting, and it significantly saved the time to create the drawings from the 3D objects. Based on the time that you will spend to set up the multidiscipline drawing to create all the templates and batches, you can get a result with just one click in theory and in perfect world. Of course, you will need more than one click, but it will save a lot of time, and result is very good. Also, one of the things that we are working on is O6 Exchanger. O6 is open class 3D Exchanger when we are doing on the importer and exporter. So when something needs to be sent to the, I don't know, class society or to the customer, it can be done in O6 format and can be readable by other viewers or softwares. But also when we get something in O6 format and we have a beta stage closed for importer, intention is to get data that will be CATIA native, so we can continue to work on it. Also, here is mentioned CATIA Composer because we can do customization and configuration for the customers. because customers often need something to be able to show to their customers. So our customers have their own customers, and here's the product, and when they have special needs, we are helping them to achieve it. Not in this case, but in some previous cases, we are often using CAA to create those modules that are needed. Here are some of our references, but it is not needed to be shown now. About reverse engineering. I will talk a little bit about reverse engineering and about digital twins. Speakers before me already told a lot about that, so maybe I will repeat something, but it is like it is. So reverse engineering, 3D scanning technology, digital twins, and then I will show you some examples of 3D scanning and results that we made in our company. Basically, as you probably know, reverse engineering is a process where existing product or component or system, whatever it is analyzing, and the goal is to understand how it works and to be able to reproduce it. Why it is needed to be reproduced, it will be shown later. Main advantages and reasons to do scanning is to create a CAD model for the reference or for the future reference. So we need to explore existing design, to understand it, to build a new model, and then we can, on this digital model, discover any weak points of the existing structure or whatever it is. But not only that, we can reconstruct a product that is outdated and that does not match modern needs anymore, but can be made better. But also it will help us to get new ideas based on the old products and to get more efficiency to come to the market. So, key steps of reverse engineering is, of course, you need to have original model or component to scan it, process it, and to get a prototype. So first, like for any other project, scope must be clearly defined, and then 3D technology must be selected, whether it is photogrammetry or laser scanning or something else. Then object must be prepared. That is very important because you have to remove, if it is possible, any obstacles that will impact the result of the scanning. And also you have to add markers to be able to register your scans and to overlap them. Because if it is huge area, of course, it cannot be done in just one with just one scan. Then 3D scanning itself, data registration, and modeling based on the point cloud that is output of 3D scanning. After that, quality control can be made. You can to check versus real model, if a real object, if everything is there, and then documentation can be built. And if needed, based on the purpose why that scan is made, some post-processing like rendering, getting nice pictures or videos can be done. And of course, for 3D modeling and creation of 3D modeling, if we can choose the tool, we are using CATIA 3D Experience and CATIA because we are working with it. There are lots of applications, and if anyone from civil industry will do a list like that, like this, it will be different, but some of the main tasks on this list will be the same. So first of all, if you have correct model and as-built documentation, you don't need laser scan. So if you don't have, and usually for older building structure components, it doesn't exist, as-built documentation must be done. Then infrastructure assessment for older, let's say, bridges or dams or something else. With aging, you need to know if it is still required, if it is still good, if it still match safety requirements. And also failure analysis. If infrastructure assessment wasn't done before and something bad is already happened, with 3D scan, you can it can help to find the root cause of the failure. Of course, modification and retrofitting and historical preservation and reconstruction. So if you have some important old building, documentation for sure does not exist. So to reconstruct it or to preserve it, 3D scan is needed, because first you need to have good documentation to start with the work. Similar is also for process industry. It is a little bit different, but not too much, because customization and retrofits are always there, same as process optimization. But in this case, regulatory compliance sometimes asks for new systems or existing systems to be improved. And in that case, legacy systems must be incorporated together with the new one. There is no need to start from the scratch with everything, just to change that that needs to be changed. Also, quality control. After some years, you need to check if everything is still as it should be. Documentation and data recovery, because during the usage something probably was made, and question is if it is properly documented. 3D scanning technology, I already explained the process of 3D scanning methodology. So first, in this case, this was a boat. It is physical shape. Then point cloud is produced with the 3D scanner. That point cloud is processed, and everything that it is not needed was trimmed out from the point cloud, and then in this case hull must be redone, and it was done in CATIA. So this surface is based on the 3D scan, and it was done with CATIA. And basically for all objects, those are the main steps, and process goes like that, based on the size of the object and type of the object. It is a little bit different, but those are the main steps. As I already told, there are lots of advantages. First of all, you don't need to work directly on some huge objects, but you have a 3D model, and you can build a mock-up and new systems, all retrofits and modifications on the model, and to have understanding what has to be done, what has to be changed, and therefore you will save the time and money and material, of course, for the modifications that has to be done. And with 3D experience, as I said, we are using 3D experience CATIA modules for 3D scanning and for reverse engineering based on the 3D scanning, and based on that what has to be done, we are using different modules. Sometimes only surface must be created from the point cloud, but sometimes we have to use part design or even fluid design when all the pipes has to be created and be ready for production. Then, of course, only part design cannot be used, but some other modules. About digital twin. Digital twin seems to be similar to the reverse engineering, but it is, of course, much, much more. Because model that can be produced by reverse engineering is just starting point for the digital twin. In digital twin, there is data integration, so data retrieved from the sensors or other sources from the real object is incorporated in the digital twin. Therefore, based on then data, some real-time simulations can be done even before the building in or object in real life is made. It can be monitored and controlled, and based on historical data that is collected during the usage of that object, some decisions can be made, and that decisions help us to, that data and historical data help us to do analytic and to make a better decision. Of course, interconnectivity, because several digital twins can be combined and communicate with each other. Creation steps are here. As I said, always objective and definition of scope must be done. Then source of data must be identified to be able to use it in digital twin. Platform should be selected. It can be CATIA, and usually it can be, yes. Then model should be created, depending if it is started from the scratch or if we want to digitalize something that is already exists, then reverse engineering is needed. Then data collected from the different sources from the existing building must be mapped. Real-time data feed is based on those sensors. Then we can go with simulation, analytics, and machine learning and visualization that help us to understand how it will work the best without building many models, mock-ups, and it can be all done digitally. Then we have to test and validate and then deploy and start to use. Of course, then some trainings for the user that will work with digital twins must be done. It has to be maintained, update, and if needed, integrated with other digital twins to have to work together. I already said about lots of benefits, so I will not read all that. We know already that it helps to make a good decision, to simulate all the possible processes and choose the best one. It saves the money because it reduction costs. Real prototype can be done better and maybe even faster. And all simulations is done on a digital platform, not on a real model. Then second part of benefits are quality, because quality can be better because you already know weak points on the digital model, and of course that leads us to the safety. Big part of that is sustainable design. with digital twin, because today I think lots of people, at least in Europe, think about environment and will rather go to the product with the sustainable design than with some other that doesn't care about our environment. So with digital twin, we can achieve sustainable design. We can see what effects does that object that will be done, what effect does have to the environment, but also help us to do the urban planning and smart cities. Because with sustainable design and with digital twin, you can connect several digital twins to urban smart cities. And now I will show you a few examples of 3D scanning that was done by our colleague in ITAC. We already talked about benefits, so I will not explain that again. I will start the video. So now you are looking at one point cloud that is done for hydroelectric plant. Problem was that after I don't know how many years of usage, question was with aging, does that tunnels can accept full flow of the water that goes through it, and will it be damaged by the pressure? So we did scan of complete tunnels for this hydroelectric plant, and this is the result of point cloud. After that, simulations were done, and I don't know what was the result, to be honest. I think it was good. Okay, so we can go on, I think. Okay, here is also a video of point cloud. Yeah, line. So it was interesting. So in this case, it was process industry, wine production and storage facility, huge one. I think it was not only wine, but other beverages also. And they want to redo it, to modern it. So that's why we need to scan, complete this facility, and to do some reverse engineering for them to understand what is the situation at this moment and in which direction they will go. So this is that point cloud that is outcome of that scanning. Okay, I think we can go on. Here is an example when main engine has to be replaced for one ferry, and it is interesting because of this tolerance for the shaft that has to be less than 0.5 millimeter. And this is rather a huge area for scanning, bigger than this room for sure. And tolerance was less than 0.5 millimeter, and we achieved to do that. So it was done, and based on that, we did in CATIA redo that main engine room and positioned new engine at its place and produce drawings. So if that has to be measured by hand or, I don't know, directly bring it there, it will be disaster, let's say. There is no better word. So this is one water treatment system retrofit. When we did lots of like that, because new regulation is now, and so we had to scan the engine room to check existing data that is scanned, and then to integrate it new system, and to keep modification of existing systems on the minimum. So that is one of the common work last few years. Of course, 3D scanning can be used for collision control to check if something new is designed by the existing documentation without 3D scanning. Sometimes it is clear when you go to the facility that situation is different than on the documentation, and then for already made models, 3D models, still digital models, we have to scan to compare the data and to see if there is clashes, and in these cases you will see that there were clashes and some changes should be done. Here is just a list of some of our references, main references. It is much longer list for the 3D scanning, and thank you.
Thanks to both of you. Test, okay. Any questions? No questions, everything was clear. Thank you once again, Marin, Nicolina.
Thank you. If there are questions after, we'll be around.
I think it's a break. Yeah. Yes. So we'll have lunch for 1 hour, 1.5 hours. Yeah. Lunch when we're back. 1 hour. 1 hour lunch, just in front of the room. Take your time to eat something, drink something, and talk with each other. I hope we'll come back in 1 hour. Thank you.
are in the meeting now.
From England team? From our side? In CATIA brand?
Yeah. Yeah, no, you're not following?
Nobody.
Nobody?
I don't know. I don't know, to be honest.
Okay.
Non, pas trop, non, du coup, parce que je posais la question par rapport à ça, en fait, mon collègue, il sera via Zoom, je vais la première partie. Oui, on le verra pas vite, mais par contre, on verra sa présentation.
Mais il présente sa présentation, elle est à distance aussi, la présentation
Allez, sur les deux en fait. Et c'est la question que je posais à Robert, c'est est-ce qu'il vaut mieux que lui, il ouvre le Zoom et il partage son écran et il présente lui-même et il bouge le slide, ou est-ce que c'est mieux que ce soit moi et... Okay. Bah ouais, parce qu'après, dans la deuxième partie, on va pas trop avoir ce problème de performance, que c'est là, des choses comme ça.
Yes, unfortunately, I don't do nuclear.
Ah,
That's
okay.
the only thing that isn't in my remit.
Okay.
It's all of IEM, all of AEC,
Yeah.
all of CMPS, apart from nuclear.
Oh, okay, understood.
So that's on my slide, IEM, AEC, CMPS minus N. That's what I put on my So unfortunately,
Okay, I didn't know in fact.
I've had a couple more CVs through.
Okay, cool. Ah, yeah, okay. Oui.
I'll send them through. At some
Yes,
point.
yes, thank you.
Have you had a look at the other?
No, not yet, but now I will be able to have a look.
Thank you.
You're welcome.
Is there anything that we can help them? Although I know they are
They are not
huge.
using CATIA?
They are?
Not using CATIA
I know,
at all?
PLM only.
PLM only?
Yeah.
They are already on detailed design?
Hmm.
And,
But regarding PLM, is there anything that we can do? Because we are working a lot with the EPZ, which is also a nuclear power plant in the Netherlands, and we are working on lots of things regarding automation.
EPZ, okay.
Yeah.
I remember. But so they migrated from V4 to...
V5.
our Vice President for the high-tech industry and opening the next sessions about gigafactories and data centers. Please, Stefan.
Do you have a microphone? Maybe behind you.
Yeah, no, not that one, but this one.
Hello. How are you all doing? Good. Can I maybe, just as a way of introduction, first of all, my name is Stéphane Serrault. I lead the high-tech industry at Dassault Systemes. So you're probably familiar with Dassault Systemes, right? Okay. We cover 12 industries globally. Historically, we've been in the transportation and mobility, aerospace and defense. And over the past years, we've expanded to 12 other industries, and I lead the high-tech industry. And to give you an idea, it's around 10% of our sales which are done in high-tech. Just as a way of introductions, could I just have maybe a show of hands of where you come from in terms of geographies? How many of you are from Europe here? Okay, so a bulk of you. From Asia? You're not sure, is that right? They're from the UK. Okay, okay. So total disclaimer, I'm half British, half French, so I feel your pain. How many of you are from the US? Okay, just so I can manage your jet lag. Okay. And from Asia? Okay, great. Okay, how many of you are French? Okay, good. Great. Nordic? German? Okay. All right. I'll stop there. Great. So it's great to meet you. And so I want to take you through a little bit the journey of high-tech, and I'll start very simply with, well, what is high-tech? High-tech, and what is high-tech for in general, and what is high-tech for a Dassault Systems? So the approach we take to high-tech is really, let's say, from the chips, from semiconductors, all the way to connected systems, which are typically electronic systems. Think about your iPhone, think about your dishwasher, think about your computer, all the way to digital infrastructure, which is the wider digital environment we live in particular with data centers and networks along the way. So some of you, is this, are we on Zoom too, Olivier? Okay, so, well, thanks a lot. I'll be concluding now. Is that right? So if you look at this, you're probably wondering, well, I'm actually in the wrong session here. I'm in the infrastructure workshop here today. But I will take you through a little bit how from electronics, effectively, we have taken a journey which really takes us to the world of infrastructure. But before I do that, I just want to highlight for each of these items, from semiconductors up to connected systems and digital infrastructure, for each of these elements, Dassault Systems has a groundbreaking practice and solutions to be able to help design, build, and operate everything from chips to batteries to connected systems and digital infrastructure. So chances are that your phone has been designed or simulated using some of our solutions. Chances are some of the 5G antennas that your phones are connecting to or are connecting through some antennas designed with our solutions. The 5G beam could have been simulated with our solutions. Chances are that the chips within your phone have some component which has been designed or assembled with our solution. Now, that brings us to infrastructure. And so for each of these four elements, effectively, well, you need to build them. And so we've built a digital continuity from the end item itself, the chip, the battery, the connected system, or the digital infrastructure, to the actual, let's say, factory that allows to put it together. So connected systems, with our solutions, you're able to actually build, model, simulate the actual factory. In the case of batteries, which I understand, Olivier, you'll be looking at later today, you'll have a special session focusing also on gigafactories with Nicolas Vallin. Okay, so gigafactories are being built all over the world to be able to produce the batteries that will be effectively powering your phone or most likely powering your car. We use a systems of systems approach to be able to build and model these gigafactories. Semiconductors. So semiconductors, you might know there's a huge load of public and private investment taking place in the field of semiconductors and building the new foundries. You might have heard in Germany about the project by Intel or by TSMC, for example, in the US and in the rest of Asia. So many foundries being built, and this is something that we are working on also. And the point that I would like to take today to illustrate all of this is digital infrastructure and particular data centers and how a systems approach can allow to build data centers faster, better, and more efficiently. So I'll pause there. Any questions at this stage? So first of all, these four, let's say, building blocks I showed you, and in particular data centers, they are really the cornerstone of today's digital economy. So you take away the data centers and the world as we know it comes to a halt. Data centers are growing extremely fast. That growth has been reinvigorated this year through the new AI chips that are being developed. You might have heard about NVIDIA's H100 chip, which is sold out for 2024. And so data centers, which were on the rise ever since cloud computing really arose 10, 20 years ago, this is really accelerating. It brings a host of topics to be discussed. There's a topic of sustainability. The data center effectively is a significant contributor to global warming. That brings us back to what the initial slide I showed you to is the reason why data centers heat up is because the chips within the data center heat up. So that's why it's also interesting to have a systems approach to go from the data center down to the actual element that brings the heat in itself, which is the chip itself. And we have this multi-scale approach to it. So huge construction growth and operation challenges going with data centers and huge energy impact of data centers as we ramp up this new commodity powering our day-to-day lives. See, it's 1% of global electricity, which could be linked to the demand on data centers. So at Dassault Systems, we've looked at this from three angles, and we've been engaging with customers, some major customers, in fact, some of the most well-known customers in this field, to say, well, how can we really engage with the outcomes and with the let's say, topics that come along with it in the data center field. And there's three of them, effectively, which will all talk to you in your domain. First of all is to be able to increase stand-up time to build them faster. This is a demand market, so you need to catch up with demand as much as possible. Every day lost is a day of business lost. Then there's effectively a very complex supply chain to be able to build these data centers and build them, bringing in all together the contractors that allow them to put them together. And then there's obviously regulation, and one element here also is the operational side. Once it's running, how do you make it? How do you operationalize them? How do you upgrade them? How do you keep them running? And this is a topic for us which really called to a systems approach, and that's what we set in motion to do. Systems approach, first of all, on a multi-scale level. So really from the chips to the circuit board down to the actual server itself, the rack, the server room, and then from the server room, the actual data center, which you could very much see as a big computer, effectively, in itself. And then obviously you could take the system wider to see how do I build a network of data centers, or how do I integrate a heterogeneous fleet of data centers, of co-location space, of other redundant data centers along the way to be able to ensure that the end customer gets the quality of service that he wants when he's calling in a web page or a web service. And this systems approach, when we take it to the infrastructure level and you break it down effectively, you got to put together, there's the power systems, there's the cooling systems, there's the IT systems. So there's the multi-scale approach, and there are all these systems to be putting in place into a coherent self. We've drawn a lot of parallels to this to actually look at what we've done, for example, in the aeronautics industry. The example here of a Dreamliner is how you put together a very complex set of elements together to be able to put a robust service in place. Okay. So I quite like this video because it zooms in a little bit like when you zoom in on Google Earth and you really start with a geographic perspective and you zoom in on all the service here down to the simulation of your compute room. And so you've got the cooling systems here. And so the way we've been able to engage with our customers around this solution is really from the compute up. So really start with a need. Don't start with a box saying I need a data center which is, you know, the size of a football field, but I don't really know how much compute I'm going to get. Start with a mission at heart and say, well, I need this much compute for this much region to serve this much latency to this customer, for example, and then build it up from then to the optimum data center facility to be able to meet that engagement. That system being put in place, the collaboration around all these stakeholders, and they are complex, is another element where we've been putting in play and saying, okay, I figured out what I want to do in terms of compute. I figured out what would be the ideal, let's say, frame to be able to put that in place. Now, how do I actually start engaging with the right value network to be able to bring that together into something which I can actually deliver? And then we've put together a solution set. I can actually, this is something which you can actually see. It's online here, bringing in together all of our processes to be able to deliver and build this solution. Okay. And so all in all, we're confident with our solutions that you can reduce stand-up time, reduce energy consumption, and really improve the maintenance productivity along the way. And so what I wanted to have a little chat with you all about is this example I gave on data center. Effectively, we're seeing the same momentum on the foundry space in the semiconductor sphere with the Gigafactories, which you'll see later today, and with the new high-tech products that are being launched, not just consumer electronics, but increasingly robots and other elements which are being put in place through massive industrial complexes. Any questions? Are any of you working on these, on similar kind of projects? Go ahead. Yep. Yeah. Yeah. Well, typically, I think one of the topics that they find is it takes a lot of time, everything from the permitting down to actually getting it running. And would these be co-location companies, or they would actually operate the data center? Yeah. 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 Right. 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 So an outcome-based approach, and I think that brings that ties in very well with what we're showing here, because you start from the outcome-based approach. You say, this is the uptime I need, 99.x or something. And then you build your system from there and make sure, how do I meet, my main constraint is meeting that uptime, if anything. So I think that could be a great place to start. Start from the uptime to the build, designing your system requirements to meet that, and then go to the build later on. You had a question, maybe? No, sorry, I saw a hand go up around here. Oh. Any other questions? Are any of you working in the battery space? No. In the semiconductor space? Yeah, yeah, yeah. I think in the semiconductor space, often the problems are a bit different. Speed to market is very important, obviously. So you'll all hear, if you read the news, being able to build your foundry quickly is important. Training staff is also a real challenge in the semiconductor space. So having effectively, once you've designed your virtual twin, being able to train people within it can really make a difference so that you can speed up your arrival to market. Yes. Yeah. Yes. Not at all the same. You're right. Yeah. Yeah. Yes. Yeah. Yeah. No, absolutely. Very true. Any last comments on your side?
Yeah, one comment for me. Yes, it worked. Yeah, for me it was really important for you to figure out what is our vision regarding high tech, and then we will deep dive on two main topics, so gigafactories and then data centers. Why? Because what is really important, it's so this morning we discussed a lot about the process industry mostly, or linear infrastructure, then process industry. And in fact, what we are able to do with gigafactories, and then Baptiste and Nicolas that will then they take the lead, we talk about that, it's to connect the product to the process to the factory. And this is something that is really key because most of the time, most of the customers, to be frank, you have, and this is what we saw as well at ESS for some historical reasons, because the project started many years ago. But you have Revit for the building. You have mostly potentially Viva for systems, etc. But how do they work together? And the problem is, if there is a change on the system and the building is not aware of, it will cost millions of euros for a change if you are not being able to correctly aggregate and communicate. And we have a good example recently on a Gigafactory topic where the product change, the process team was not aware. Millions of euros for a change for the process. But then changing the process impacted as well afterwards the building by itself. And again, millions of euros. So this is where being able to connect those different layers together is really key for us. And this is really the purpose of the virtual twin, defining, modeling, and simulating in order to be able to connect those three layers. And so this is why it was important for us to have you on board. Thank you.
I think that's a good way of summarizing. If you should ever remember something here, it's the 3 Ps: product, process, plant. So really making sure that, obviously the plant, the product, so in this case, the product, is the chip, for example. In the case of a gigafactory, the product is the battery. In the case of consumer electronics, could be the end product, then the process and the plant, and building that continuity.
It opens new horizons. by engaging on modularity as well.
Yes.
Modularity for being able to change efficiently the production, whatever will be the request, to be more sustainable, to be more efficient regarding energy consumption, CO2 emissions, etc. This is something that is really important, and this is where, in fact, you will see why CATIA, because most, to be honest, when we started working together maybe 2-3 years ago, when we think about manufacturing directly, everybody is thinking about EMEA. No, but you need to anticipate. And your production line, you need to define the reason why you need this production line. You need to understand what will be the problems, how to solve those problems, and based on that, being able to define correctly the production line and to size efficiently your plant or your data center regarding the number of racks you will have to deal inside, etc., etc. So this is where the systems engineering approach as a skeleton, in fact, for the virtual twin is becoming more and more important to anticipate and then afterwards capitalize.
Great. So thanks again, and have a great seminar.
Thank you. Thank you, Stéphane.
Merci. Merci.
So now let's continue with Baptiste and Nicolas. So Nicolas is on Zoom.
Yes, he's connected.
I hope now it will work. Yeah, but I'm not sure mine.
Thank you. I think you said all.
Hmm?
You said all already. You can close.
It's because we are late. Okay. Okay, I'm sharing. Tac. Perfect. And Nicolas, are you with us?
Yes, can you hear me?
Yes. Cool. Thanks, Nicolas, for waiting for us. Sorry for being late.
No worries, thank you, Olivier.
Stage is yours now.
No, it's okay. So you will speak. Okay. Thank you all. Now let's deep dive more on modular and agile factories. Yes, after this session previously, we will deep dive on Gigafactory first with my colleague Nicolas, and after I will extend the topic more of smart factory. Yes, with example of Gigafactory, but not only. I introduce in 2 words, I'm Baptiste Cousinery. I'm part of CATIA brand for value engagement globally in infrastructure and specialized in factory. So I'll let you the end, Nicolas.
Thank you, Baptiste. So hi everyone, my name is Nicolas Valin. I am working in the transportation and mobility industry team as a business consultant, and I'm focusing on battery projects for our car makers, customers, or EV battery customers. So today we'll speak here about gigafactories, but first with my transportation and mobility angle, I'd like to share this view. Some of you may be familiar with this transition towards electromobility that is driven by regulation in most of the regions in the world. And what you see here is the outcome of this change and the speed or the pace of this change towards battery electric vehicles, not only, but mainly. And what we see here is that not only this transition is happening, but it's happening super, super fast. Customers want EV batteries, the volumes are there. And the challenge now is on battery makers because these guys have to deliver the amount of batteries required. We talk about thousands of battery cells for each car. And considering the number of cars on the road, we'll have, battery makers will have a huge job. But also the amount of money that is spent in this industry is tremendous. So numbers are given, different numbers, but what we have collected is that roughly $1,200 billion will be spent by 2030. So if you go next, the key thing here is that this great transition comes with a lot of challenges. And what we see are, let's say, 3 buckets of 2 challenges. The first two on top about product development, the way to manage the complexity of batteries, and the way to keep track on the innovation with all the new technologies that we hear, new batteries with solid state, new batteries and sodium ion, and all other innovations that we see in the market. So first pair about product engineering. Second pair of challenges, this is where we will focus on for today, about delivery, dealing with capital projects of gigafactories, so the core of what we will see today, but also shortening the time to mass production. We talk about here about projects that are 2, 3, 5, if not $10 billion per project. So customers want to make sure that the money they will spend is well spent. And ultimately, the last pair is about the ecosystem. No single battery company can do it alone. And the need to work together, of course, complying with regulation is very important. So you can switch. And considering those challenges, the way we have articulated our strategy is around 2 virtual twins powered by the 3D Experience platform. The first virtual twin to help battery companies deliver the right product to markets with the virtual twin of the battery, saving time in the way they go to market. And the second virtual twin about the profitability of the company, making battery gigafactories a successful project with the virtual twin of the gigafactory. So those 2 virtual twins powered by 3D Experience platform, and not only powered by, but also connected by 3D Experience platform, where we also want our customers to ensure the scale-up, connecting engineering, manufacturing. So if we go into more details, yes, about the product development, we are covering a full range of product development, all the way from chemistry or formula of battery cells to, of course, battery cell design and simulation, battery pack design and simulation, and with 3D Experience, the ability to deal with the trade-offs of those batteries. Now, product, but also process, from the way we understand what's going to happen on the materials aspects during manufacturing process, to the way we develop the manufacturing process plan with all the steps, the way we design the line, we commission the line, and we run simulations. And ultimately, talking about the factory, where we are connecting the way people are developing the gigafactory on different layers, from the line, the equipment, the line, to the gigafactory systems with system engineering BIM. And of course, operating the factory, where we have a dedicated offering for that. So you see here those 2 virtual twins and the complete scope of our battery offering. If you go next, we will focus here on the virtual twin of the gigafactory. So you can run the video. And what we mean by the virtual twin of the gigafactory is actually a threefold. First, starting with the operations engineering, which means the way the gigafactory will be engineered. And as I mentioned, it's about different layers, from factory system in its environment, to the manufacturing line, to the equipment itself, and even to the resources, from human resources to AGVs that will work on the shop floor level. So dealing with this, with a 3D context of the gigafactory, to then optimize the layouts, the overall layout of the gigafactory. So it's a bit fast here because it's a lot of equipment to place, but really the purpose is to converge with factory development and process development with concurrent engineering. So optimizing the layouts with 3D, so that you are able to run simulations and try out scenarios on the way you want your layout set up. This enables you to identify potential bottlenecks on some elements of the line, but also try out maintenance scenarios, try out different location of your equipment, and perform hours, days of simulation of running the factory way before you actually build the factory, so that you are able to minimize the mistake, reduce the errors, and of course, limit the rework. Once the operation engineering is done, it's about operating the Gigafactory. In this regard, we are working with our manufacturing operation management solution called EMEA Apriso, where not only we help execute manufacturing operations, but also working on the global orchestration of the battery manufacturing process. And what do we mean by the global orchestration? We mean that it covers a wide scope from quality management, so we see a lot of quality issues in battery manufacturing, but also warehouse, but also maintenance planning. And the unique, there are two actually unique values that we deliver here. Is first this ability to connect these global operations with the operations engineering at first, and second, this ability to replicate this manufacturing operation management system into other lines or into other gigafactories. So now it will be about the third pillar. So we have designed the factory, we are operating the factory, and the first point about collaborative operations is to get the best of the real world and the virtual world. So what we're able to do is to put the data collected in the shop floor in the context of the virtual model, so that we're able to learn much more quicker about what has worked, what didn't work in the shop floor, how to replicate golden batch, how to understand why this is a golden batch. And the thing is, putting this data into the context of the factory helps understand and helps go through continuous improvement and ramping up factory operations. So some of you may be well familiar about the challenges behind ramping up a battery cell gigafactory. So if you go next, Baptiste. In short, quick summary, we have this industry solution experience called High-Tech Smart Factory around those three pillars: production engineering, operation management, continuous improvement. And if you go next, there are three main points to have in mind. First, mitigate gigafactory project risk. It's very costly, and we want to make the best out of the money that is spent with process and factory concurrent engineering, defining new ways of working, of collaborating between those two different groups. Second point, the collaboration with ecosystem, not only equipment makers, line builders, but also factory contractors, and having an holistic way of integrating those equipment, but also those systems into the virtual model. Third, it's about ramping up the Gigafactory with EMEA Apriso Industry Province MOM system. You can click, and within this high-tech smart factory industry solution experience, we are covering different processes. And I think now Baptiste will focus mainly on the infrastructure aspect with facility concept design, industry process experience. Baptiste.
Exactly. Thank you, Nicolas, for this overview about Gigafactory. Yes, I will continue now to focus with our solution, and particularly we will find this solution inside the VIP described by Nicolas just before. But before discussing about our solution, it's important to understand the context and the challenges. I won't detail a lot of these challenges because we talked already about all of this with Nicolas and previously with Stefan. But what you need to keep in your mind, sustainability, smart production, and the scale-up is one of the most important things. Of course, improves the productivity and quality with a process stability. But what there is behind all of this, technically, concretely? Some feedback. It's a list of challenges, not exhaustive, but it's just a part of them. receive mainly from customer feedback. First, how I can optimize my existing production line, but taking into account at least the less expensive technical choice. How not to be document-centric, to be data-centric. How I can aggregate a lot of different data from different sources. And in the end, to have the link with my requirements and to obtain the impact in the level of my production line, but also to my factory building behind. How I can optimize my collaboration, not only externally with the huge ecosystem, as you imagine, around the factory, but also internally, between construction department, between engineering, between manufacturing department. How I can make some production line layout and to do some simulation when I take into account some existing building. How I can anticipate some impact, how I can do some scenario in advance before building my factory or when I am building my factory, and to avoid to do directly some real test on site or to modify after. And not only the building, one important thing, when we speak about building in factory, we speak also about the systems, about the network. That means behind electrical, plumbing, HVAC, and so on. All of this need to be taken into account. And this is the case with our solution. And after the last, it's the reuse, the replication. Gigafactory, it's a good example. The particularity of a Gigafactory is a replication. We are doing a first production line, and after we replicate this production line in many to obtain inside, in the end, the factory. We are not doing a factory from scratch and we put on when it's finished in 100%. No, we have an intermediary production line. The target industries, it's just to understand also, we are speaking, like here we spoke about the Gigafactory, but in fact, I am not speaking only about Gigafactory. I am speaking about the smart factory. So we speak about discrete or continuous manufacturing and in different industry, quite all in fact, life science, but also for car manufacturing, aircraft manufacturing, high-tech, and so on. And we have the two kind of situation. We have, like for, it's a good example, Gigafactory, greenfield factory. Greenfield, that means from scratch. We begin a complete new definition, a new site, new architecture, new design, new building, and so on. But we are speaking also about the brownfield factory. And it's important because in Europe, in Asia, the country, you have already a lot of existing factory and not some new project from scratch. So we need to take into account this possibility. So you have an existing infrastructure, an existing factory. They want a virtual twin. They want to modify. They want to extend because they have a new product or so on. And so behind, you have the concept of reverse engineering and 3D scan. The scope also, we talked before about product process factory. With CATIA, we are speaking, maybe quite obvious, but about infrastructure, the factory itself. That means it's a container. The content, I like to say, it's more the production line. It's more the manufacturing level, the shop floor, with behind lots of concepts from EMEA. And after you have the product. But after the key, what said Olivier before, what is key, it's how to connect the product to the process, to the factory. But we are really speaking about factory level, how to put in place my factory in a region, in a site already. And after, we deep dive, plant layout, conceptual design, detailed design, virtual commissioning, and so on, in collaboration. So now, let's see what we are speaking. You have three key concepts. It's an overview. I won't go to the detail because there are some video just behind. But you have three main steps. The first is the model-based approach. It's really important to understand that. We spoke this morning about system, and yes, the factory, we need to change our way to address. We need to think a factory like a system of systems. That means the factory itself is a system. The production line is a subsystem, and the equipment is also a system. And this is very a different way of approach. This first video, I will introduce the first video to show the CATIA virtual twin can be used to define and to design the Gigafactory. And it will illustrate how we can define, manage a Gigafactory like a system of systems through system architecture and the requirement management. In fact, here you see the factory. It's not only a Gigafactory. Here it's a Gigafactory example, but it will be in a factory implemented inside a region. That means we manage, we define the project from the beginning of the project to the end of operation, and the goal is to define the Gigafactory inside its environment and with the link with the local authority. It's important because you have different buildings and you have civil infrastructure behind. We are not speaking here about 3D BIM approach. We are speaking about system engineering, BIM system engineering, because you have different modularity. In the same environment, before you saw the Gigafactory in the region, and we can zoom in the same environment in the level of production line with different equipment. But we can also focus to the equipment itself with all attributes, all document links. So, in fact, you can obtain all modularity level in the same environment without discontinuity from the factory to the pilot line to the equipment. And like this, you put in context all the data in relation to the factory, the size, the pilot line, and that's why we are speaking about modular design and with a speedy integration approach. But before that, important things, we need to define the requirement. It's very key in the approach of model-based. So here you can create, define, unify all your requirements between them inside what we call a requirement structure or a master data. After this step, we need to manage. After this definition, the solution inside the 3DX platform can allow to link the requirements between them with design data and to visualize the progress when you incorporate some new requirements. Like this, you can improve the design quality by ensuring that all the requirements are integrated inside the production drawing, for example. You can ensure the consistency of the requirements and also you can follow, of course, the traceability of the requirement along the life cycle of the definition of your factory. The last step is system engineering. System engineering, so it's the definition of the system architecture. After the definition, organization of your requirements, you can create what we call a PBS, a product breakdown structure, and organized by function. All your systems are organized by function. By this way, your systems, your subsystems, are linked between them. And like this, you can manage the development of your function. You can define cross-discipline also approach, HVAC, ELEC, and so on. And we will see after to do some design collaborative review. We saw the first part of model base. Now we continue in the process to see what we call a facility virtual twin. Behind, you have the concept of 2D, 3D, technical handover. That means to do the link between you, customer, as an owner-operator, where you operate your factory. You need to do the link to collaborate with different suppliers who can use different tools. And also I have added, this is a particularity versus Gigafactory, a part of reverse engineering also. When you have an existing factory, some customer, they ask us, how I can reuse my data. I don't want to design from scratch my factory. So through this second demo, we'll illustrate the facility virtual twin with the 3D definition of layout, the process engineering with 2D, and first important point, how we can reuse through reverse engineering. So in the first part of the video, so let's see after a 3D scan of and to have an import of cloud point, we obtain a building and how we can reuse this. In fact, voilà, you can create your model with the number of points what you want, and after you can do some remodeling. That means you extract some area and you can delete what you don't want, some machine. You can keep only what you want to see, and after you have an automatic recognition of different surfaces like walls, cylindric, like a tube, and after you can do some remodeling on top of this with the texture, the wishes texture. You can have all the details and you can do the link with an existing library, the existing catalog. Here, you can have also some automatic recognition and extraction by color. And if you have in your library already some item, you can have also a direct link with your library to recognize. And you can do also, like here it's an example of a pipe segment, you can do some automatic remodeling on top and to win a lot of time. When you did this, when everything is integrated, you can reconnect, in fact, with the process standard we defined before. That means the system engineering with PBS and also with the 2D, the 3D plant layout. And here we connect with the 3D plant layout. So if we speak about this, first you need to create some main space to know where you will put in place your main equipment. And as I said before, all 3D models are always in the same environment. On the left, you can see the list of requirements, the tree, RFLP tree. With this solution model-based approach, that means your factory is organized not only in 3D but by systems and subsystems. And like this, you can simulate very early in the design phase the different scenario you want to do. And like this, you can do some design choice, and also based on the schematic already inside PNID, block functional diagram, principal functional diagram, and so on. So you have all your requirements and function and system already defined, stored in the 3DX platform. This is the referential, the unique source of data. It's linked to the 2D schematic, PFD, PNID, and so on. And you can have this traceability among the process. The 2D are linked to the 3D. With a synchronization, you can link the 2D and the 3D. So that is the virtual twin. 2D linked to the 3D, associated to the requirement, organized by function. In the end, you obtain the process and facility virtual twin. I will finish this demo with the collaborative design review. When you have all this data inside the 3DX platform, but another important point inside your virtual twin is how to collaborate all together, internally and externally. You have different suppliers. They use some other tools. Let's talk about Revit, for example, for the construction. In fact, to collaborate, you can import all the data you want. when they respect the standard IFC. And it's very important for the design review because as an owner operator, you can always say, oh, the detailed design is not my part. I delegate. I subcontract. Okay, but in the end, you are always responsible of the specification and definition, and you are responsible of the management of interface. When I speak about interface, it's electrical, HVAC, all disciplines, in fact, behind. And you have many suppliers, they manage different disciplines. With the 3GX platform, you can manage the interface, the clash, and also to share the work you need to do, because you can filter what each can see. I will finish with the last part. Unfortunately, I cannot see some demo. It's a pity because I have some customer data. So I will ask you to trust me and to imagine a little bit. But we will have soon a specific demo with our own data. But it's a pity because it's interesting. It's how we can do the link with the production, with the manufacturing. Because we talk about the first part of definition of factory. We talk about, okay, conceptual design, how to do the link with your supplier and the collaboration. But now, what question could arrive? Okay, how we can do the link between the BIM and the manufacturing world. In fact, today, before, mainly is what we can see also in the market, in our customer. Construction department and manufacturing, there is two different worlds. They work in parallel. Sometimes they communicate, but they don't work. They don't work all together. That means I am part of manufacturing department. I need to modify or to put in place my production line, and in fact I do. And after I ask the construction department to do an estimation for the building, if I need to change some wall, to extend, and so on. And after, and it's always in one way. With the different solution, with the solution in the market for software, it's a little bit the same. You have the definition of the BIM, the design in one hand, and on the other hand, you have the simulation of production flow and manufacturing. So today, the question is how we can put in context all this data, all these people. For example, the simulation of production flow, it was done in 2D and without a context of building, list of machine and parameter in input data and just the shape of the building, and that's all. Today, what we put in place, it's let's take into account the BIM, and it's very key because what happens is finally in your simulation of production flow, you have a wall in the middle if you don't have electrical production near and so on. So today, with the EMEA solution, take into account the BIM context. So we have the production flow in the middle of the building and all systems around. And this, it's quite a key because now you have a concurrent engineering between the construction department and the manufacturing department. So the building and all constraints of pathway, for example, are taken into account. I will finish with the last slide. If you need to remember about four things after all this long speech, it's efficient definition through model-based approach for virtual twin, differentiator, key. We can quickly develop a layout from the beginning in the building model. The connection, I repeat, it was already some teasing about this, but yes, how to connect the product to the manufacturing to the factory. That means with this solution model base, you need to imagine we have a new product or we need to change the level of production, how we can see the impact in the end, yes, to the manufacturing, but also to the building. and modular design and speedy iteration approach. Any question? Seems clear.
No question? Okay. Okay, thank you very much, Nicolas. So, don't remember which one. Okay, this one is working, perfect. So, after this example of Gigafactory, let's move to another factory, so on life sciences, because we talked a lot about modularity. And typically for biopharma, this is crucial. This is something that is already deployed on many customers, so such as GSK, Johnson & Johnson, or Sanofi, etc. And this is really interesting to see, in fact, what does it mean for biopharma to be modular. And we will talk about a specific use case that is to deal with single-use equipment in order to reduce the environmental footprint, etc. They made choice, meaning being able to use single-use equipment to connect modules together. So this is something that we will talk about with the next speaker as soon as we can start the Zoom. Clément, I don't know if you are with us. Not yet.
You are in the meeting now.
Hello, Clément. Clément?
Salut Olivier.
Ouais, cool. Thanks, Clément, for joining. I was so we just finished the session about gigafactories, and I was doing the transition for you regarding the modularity aspect on biopharma. So stage is yours, Clément. Thanks.
Cool. Thank you, Olivier. Can you see my screen?
Yes, I still see my part of my screen on yours, but I don't know how to remove it. Maybe I need to give me a second. And no, you have a blue screen. It's not. Let me 5 seconds.
C'est bon, Olivier.
So stage is yours, Clément.
Cool, thank you, Olivier. So yes, first thank you, Olivier, for welcoming me to this event, and I'm really happy today to present what we do in life science and about what we do in terms of providing therapies to every patient against the clock. So one interesting fact I want to highlight first with you is this number is 1.7. So it's a capacity that will increase in terms of biologics by 2026, which is quite huge, and because like the demand is quite evolving a lot, and we see new therapies which are targeting new patients, and this is why the demand is also rising. And we can see it everywhere on the news from lots of companies, from Novo Nordisk, Genentech, Regeneron, Gilead, Merck, Lilly, and even Sanofi, who are building new plants to face this new demand, and it's huge. Like a lot of money is spent there, and which means that there is a need at some point to help these companies in this building and construction activities, and also the collaborations between subcontractors, engineering companies, and also big pharma companies. So when talking about virtual twin in pharma companies, I think you all know what a virtual twin is. It's a representation of the real, and it can represent one particular object, so which can be the product, so the molecule by itself, or the device, the plant, the process, and also the patient virtual twin. And at Dassault Systèmes, we try to be and to see the entire virtual twin environment as one, and so that product can fit the patient, process, and the product. Because in pharma, we say that the product is a process because they are quite tightly built together. And today, we will make a big focus on process and plant virtual twin.
So to help pharma companies face these challenges, to help them build faster, where at some point they need digital capabilities, and they need to accelerate this new facility launch and new process launch to also help them produce several therapies simultaneously by optimizing the changeover. And this being said, we want also to help them produce more with more agile ways and to help them change the production from one product to another quite fast. And we want also to help them transition to a more sustainable way of manufacturing through different simulation aspects and design and engineering aspects. Another number that I think is quite compelling, because I just talked about modularity, but 1 plant over 2 that is newly built will be modular in pharma companies, which is really shifting the way pharma companies saw things until I would say 3 years ago, because before you built one plant to fit one process, which means that you fit one product, and now you are trying to build one plant which will fit several products, several processes. So we shift to modular activities. And this concept has been raised by the ISPE with the ballroom concept, and I will share after a video from CATIA, where we use this concept to show how agile you can be in terms of pharma manufacturing. And Bioforum we used it and kind of developed the way of defining a new plant, and so Bioforum gave it more popular. So what is a module in pharma companies? So a module is a ready-to-use set of equipment, process steps, and single-use kits. So we see it as a one-two because one process step and one module is a concatenation of these 3 elements, and so which means that you can produce one step of your manufacturing job with this set of equipment and single-use and process steps. So single-use technology is also something that fits with modular activities, meaning that today all the equipment that are modular are fitting this technology, or most of them. But when talking about virtual twin of a module, so we want also to enrich at some point the modules, and so for biomanufacturing, which means that we want to give the possibility to pharma companies and to equipment providers to model, to engineer, but also to standardize and industrialize their processes before they even exist or even in operation, so that you can reuse or reshuffle a process that is already in use, so that you can optimize, continuously improve it by managing the process parameters, for example. And it's also a way to give it's a good way to collaborate in between companies and between subcontractors and engineering companies. And behind this concept, we talk a lot about libraries. We want to reuse because we are standardizing. In pharma, we are working with technology platform. For example, mRNA is one of them, or vaccine could also be one of them, which means that you have a base and a standard libraries of processes that can be reused from one process, so for one product, to another. We want, of course, to manage the life cycle, so life cycle of the equipment, life cycle of the process steps, and also of the consumables, and the risk associated, and therefore to manage also the change and the impact. analysis. Here is a short video about what we could do in terms of single-use design. So what you see here is definitely how you can reuse single-use components to build what we call a single-use kit, meaning that you can go in a library, so store all of the single-use equipment and build your single-use kit that will fit your process directly here in the platform, and create connection between your components, and therefore after give kind of intelligence in your PNID. So it's called the PNID, piping and instrument diagrams, so that you can check, for example, flow directions, and this also helps to communicate with equipment providers, so that pharma companies can build and design their own process and then share this information directly to the subcontractor who can build and manufacture the single-use kit. What's also important behind the platform is the fact that you can trace. So you can trace every object in the platform. And so if you have built single-use kit, which is an assembly of consumables, you can map it and see it directly in the platform, which is quite powerful to then find where the consumables have been used in other processes, for example. If you also want to go further, what's really interesting is to also make the link with the 3D. And we hear a lot from companies that they need, for example, for maintenance activities and maintenance workflow, to cross-highlight between PNIDs and the 3D, so that they can identify exactly where the parts are in the plant, and also easily find it when you want to maintain it, to order also different consumable, and yeah. But we want also to tightly unify it with what you can do in manufacturing, in a plant, and in a really manufacturing environment. So we demonstrated how you can design, engineer, and optimize the process. Now, how do you reuse and how do you use this process directly in your manufacturing environment and unify everything and optimize everything, so that you can have kind of a mod team approach, meaning that everybody is working in collaboration, so manufacturing engineer, but also process engineer, so that as soon as you see an issue, you can raise it and don't wait that you have entirely finished your process design before raising it. So we provide also several types of simulations, so capacity simulation, also flow simulation, so that you can check, for example, process cross-contamination in a plant, but also virtually commission a process, optimize the changeover for equipment move simulation, but also ergonomic simulation and life cycle assessment. So here is a quick demonstration about this concept. So obviously we want to tightly unify the fact that you are industrializing your product with the process engineering. So here the equipment that you can see on the top right are the ones that you have previously engineered, and you have this traceability, and you can find all the objects. So you can see that you have consumables on the top left, capable resources on the top right, and processes and operation at the bottom. And that we want to reuse these objects through libraries again, so that you have a standardized way of industrializing and a standardized template of processes, equipment, but also materials. And yeah, it's always interesting also to make the link with the 3D, for example, for again maintenance instructions or asset performance improvement too, and also to find where this equipment has been used in other processes. So it's a first way also to communicate. That being said, you can then link this process and the industrialization you made with so all the different type of simulation that I displayed just before, and that's what we will just see after, meaning that you can build some manufacturing process of your product, but also changeover instruction in this application, and also see the link between your changeover instructions and also the process that you have designed. This doesn't end here. Obviously, you can share this data with your execution systems and also with scheduling tools. So again, here you can see that we have a traceability, but here more at operation level and the equipment level, where you can link the requirement that you have defined previously to engineer your module with the CAD, but also different engineering documentation, such as P&ID coming from subcontractors. And then reuse this process so that you can make simulation, changeover simulation, and making sure that even before doing this changeover, you are doing the right thing, that you have the right environment settled, and that you could have the right resources doing it, because sometimes you need qualification, so you need to check that some people have the right skills to do it, so that you can plan, and making sure that you reduce the changeover time, because it's time where you are not making money too. What we want also to share here is the fact that you can also synchronize different equipment moves and also again plan and program this equipment so that they can do whatever you are requiring. Ergonomics, it's also something that is important, and even more in modular activities, but because you don't only manipulate equipment to process, but also to change the production from one production to another. So you have several cases where you want to make sure that the operators are kind of manipulating the equipment safely. And so I think so I just wanted to share this vision where everything is connected together, from simulation, so from manufacturing engineering simulation to process engineering simulation, and then we optimize everything before having an issue that can be solved. A nice use case I want to share with you is Clean Room 1, because of some numbers here. So Clean Room basically costs a lot in energy. It's quite complex to build them and to design them. So we made a concept behind to simulate what's happening in a clean room, and to optimize so HVAC systems, and kind of making feedbacks to the subcontractor designing the clean room, so that you make sure that you don't have any cross-contamination, that you have several classes of clean rooms, that your clean rooms is answering the right requirements, considering the class it applied. And so to do so, we use also our simulations. And here are some enabling changes that the platform can provide. So collaboration, consistent data model, kind of data integrity, visualization, 3D layout, which is also open to other systems, and which allows to kind of manipulate modular aspect, and saving a lot of time to market, time to scale up, and also reducing cost of implementing a new plant or just implementing a new line. And that's all for me.
Thank you. Thank you, Clément. Do you have any question for Clément? No? No? Are you sure? You definitely want a coffee break, so. Thank you, Clément. Thank you very much for your time. I know it was quite early this morning for you, so thank you very much. And so let's go for a coffee break, so for 20 minutes.
Thank
Okay?
you, Olivier. Bye-bye.
Thanks,
Have a good
Clément.
coffee break.
Yeah. Yes, we can open, yes, a bit.
On est bon. Congratulations.
Ah ouais, carrément. C'est juste après. Ouais, on est bon. Alors attends, je fais ça proprement parce que sinon à chaque fois que je me déconnecte, c'est le bazar. T'as besoin de rien en fait. Tiens, t'as besoin de micro peut-être. Et encore, même pas. Attends, j'enlève ça. Hein? Tiens, t'as tout ce qu'il faut pour connecter là. T'as besoin de. Tu te connectes avec quoi toi? Mais tu peux connecter ton iPhone. Ça c'est pour. Ouais, pas trop fort.
Oui, ils ont essayé de remonter le petit canal.
Ah ben, il a présenté un petit peu rapido le data center, l'inside out. Mais rapido en fait. Mais c'était bien au moins, sans déconner, au moins il avait préparé quelque chose de bien. Quoi.
Alors moi je suis vraiment rapide sur la partie.